Beyond the boundaries of our solar system, a vast expanse teems with incredible and baffling worlds, each more extraordinary than the last. These distant planets challenge everything we thought we knew about what a world can be. Some are rocky and Earth-like, situated in the habitable zones of their parent stars, where liquid water may flow freely, the very foundation for life as we understand it. Others are gas giants, larger than Jupiter, their atmospheres so extreme and unpredictable that they leave even the most seasoned scientists in awe. Some worlds are so alien that they defy imagination. Places where endless oceans rage, planets where diamonds fall from the sky like rain, an environment so extreme that life in forms we can barely comprehend could possibly thrive. The sheer variety of these worlds has only deepened our thirst for discovery, and every new planet we study brings us closer to understanding the infinite possibilities the universe holds. Let us embark on a journey beyond the familiar, beyond the comfort of our own solar system, to explore the bizarre and fascinating worlds that might one day become our future home. Among the most tantalizing discoveries in this vast uncharted region is Proxima Centauri b, a distant exoplanet that lies just a stone's throw away in cosmic terms. Orbiting the faint red dwarf star Proxima Centauri, which is part of the Alpha Centauri star system, Proxima Centauri b resides only 2 light-years from Earth, making it the closest known exoplanet to our home. Located in the Centaurus constellation within the Milky Way galaxy, Proxima Centauri b exists in the same spiral arm as our own solar system, the Orion arm, making it a particularly fascinating target for scientists seeking to understand the dynamics of star systems far from our own. The proximity of Proxima Centauri b has given astronomers a rare opportunity to study an exoplanet that could share similar characteristics with Earth. This planet orbits its parent star at an incredibly close distance, just 4 million miles away, far less than the 93 million miles that separate Earth from the Sun. Because of this, it completes a full orbit around Proxima Centauri in only about 11 days. Despite its closeness to a faint and cooler red dwarf star, Proxima Centauri b is located within the so-called habitable zone of its star, a region where the conditions might allow liquid water to exist on its surface. This possibility has ignited a firestorm of scientific discussion about whether life could exist there, and if so, what form it might take. Proxima Centauri b has captured the imagination of scientists and the public alike, drawing attention from all corners of the globe. Its potential to harbor life has sparked a flurry of investigations and ongoing research. But this planet is just one example of the mysteries that exist just beyond our reach. Imagine what other astonishing discoveries await us out there in the far reaches of space, planets and moons with conditions so unique that they might hold the keys to life, the universe, and everything in between. If this awe-inspiring topic excites you and you find yourself wondering about the mechanics of celestial bodies and the potential for life beyond our planet, then Brilliant. Org is the perfect resource for you. Brilliant turns complicated scientific concepts into engaging, hands-on learning experiences that anyone can enjoy. Whether you're a professional scientist or simply someone with a curious mind, Brilliant offers interactive lessons that bring the wonders of science and technology to life in an accessible and enjoyable way. Currently, I'm diving deep into Brilliant's course on how large language models, LLMs, work, exploring the intricate mechanics behind artificial intelligence. This is just one example of how Brilliant uses interactive exercises and visual learning to make complex ideas come alive, whether it's orbital mechanics like those of Proxima Centauri b, or the cutting-edge innovations in AI and space exploration. Brilliant empowers you to explore everything from the fundamental laws of physics to the most recent technological breakthroughs. So if you're passionate about unraveling the mysteries of the universe, or if you're excited to explore the latest scientific advances, Brilliant gives you the tools you need to embark on your own journey of discovery. Proxima Centauri b has sparked immense interest within the scientific community, primarily due to its location within the Goldilocks zone of its host star, Proxima Centauri. This region, also known as the habitable zone, is the perfect distance from a star where the temperature is just right, neither too hot nor too cold, for liquid water to exist on a planet's surface. Given that water is essential for life as we know it, Any planet within this zone automatically becomes a subject of intense scrutiny. Proxima Centauri b, being positioned in this ideal range, offers a compelling case for the potential of life beyond Earth. The planet's proximity to its parent star is key to understanding why it has become such a tantalizing candidate in the search for extraterrestrial life. Proxima Centauri b orbits its star at an optimal distance, suggesting that under the right conditions, liquid water could be maintained on its surface, an essential component for life to thrive. Its mass, at least 2 times that of Earth, further supports the possibility that it might have a rocky, Earth-like composition. This means that Proxima Centauri b could potentially have a solid surface where water, if it exists, could form oceans, lakes, or rivers, much like our own planet. The scientific community has also speculated about the potential for Proxima Centauri b to possess an atmosphere that could shield its surface from harmful stellar radiation and help regulate temperatures. While this remains an area of ongoing study, the combination of the planet's mass, its location in the habitable zone, and advances in technology that enhance our ability to explore exoplanets all make Proxima Centauri b an intriguing object of study. If the planet does have the right atmospheric and environmental conditions, it could provide a habitable environment capable of supporting life, an idea that has continued to captivate researchers and space enthusiasts alike. However, Proxima Centauri b's close orbit around its star presents some unique challenges. Orbiting just 4 million miles away from Proxima Centauri, far closer than Earth is to the Sun, the planet completes one full orbit in just about 11 Earth days. This extreme proximity to its star means that the planet experiences intense levels of stellar radiation and gravitational forces. One potential consequence of this close orbit is the possibility of tidal locking. In this scenario, one side of the planet could always face the star while the other side remains in constant darkness. Such an arrangement could lead to extreme temperature differences between the two hemispheres, with one side scorching hot and the other frigidly cold. These variations in temperature could pose challenges for the planet's potential to support life. Moreover, Proxima Centauri itself is a red dwarf star known for its frequent stellar flares and high levels of stellar activity. These bursts of ultraviolet radiation and charged particles could strip away a planet's atmosphere over time or drastically alter its composition. While this may seem discouraging, there is still hope. If Proxima Centauri b possesses a magnetic field similar to Earth's, it might be able to shield itself from some of the harmful radiation. Such protection could preserve the planet's atmosphere and create a more stable climate, allowing conditions for life to flourish. Still, scientists continue to debate the precise impact of these factors on Proxima Centauri b's ability to support life, making it an exciting but enigmatic subject of study. The discovery of Proxima Centauri b was made possible through a combination of cutting-edge astronomical techniques, particularly the radial velocity method, also known as Doppler spectroscopy. This technique allows scientists to detect subtle wobbles in the motion of a star caused by the gravitational pull of an orbiting planet. As Proxima Centauri b orbits its star, it causes tiny shifts in the star's light spectrum. These shifts, where the light moves slightly toward the red or blue end of the spectrum, indicate the star's movement towards or away from Earth, providing valuable clues about the existence of the planet. This method has revolutionized the way we detect exoplanets, and Proxima Centauri b's discovery marks a significant milestone in our search for life beyond our solar system. While Proxima Centauri b is still far from being fully understood, the ongoing research surrounding its composition, environment, and potential for habitability makes it one of the most promising candidates in our search for extraterrestrial life. Its combination of proximity, mass, and location within the habitable zone positions it as a beacon of hope for the discovery of life beyond Earth, though, as always, much remains to be uncovered. Certainly, here is the completely rewritten and extended version of your text in a documentary style. The discovery of Proxima Centauri b, one of the most intriguing exoplanets ever detected, was made possible by a blend of groundbreaking techniques in modern astronomy. The planet's mass and orbital period provided key insights, but these alone wouldn't have been enough. Another critical method supporting this discovery was astrometry. This technique involves the precise measurement of a star's position in the sky over time. When astronomers carefully observe small shifts in the star's location, they can detect subtle changes caused by the gravitational pull of an orbiting planet. These displacements are incredibly minute, making the process extraordinarily challenging. However, advancements in both technology and observational accuracy have significantly improved astrometry's efficacy, allowing astronomers to spot these small variations with increasing precision. While astrometry played a pivotal role, it wasn't the only method employed. Transit photometry, though not directly responsible for the discovery of Proxima Centauri b, is commonly used in the detection of exoplanets. This method measures the slight decrease in a star's brightness when a planet passes in front of it, blocking a fraction of the starlight. Though not the primary tool in this case, it is an essential part of the exoplanet discovery toolkit. When combined, these techniques provide a multifaceted approach to confirming the existence of planets orbiting distant stars, ultimately painting a clearer picture of our cosmic neighborhood. Looking forward, future missions to Proxima Centauri b face numerous monumental challenges. The vast distances involved in interstellar travel alone pose an extraordinary obstacle. Proxima Centauri b is situated approximately 4.2 light-years away from Earth, equivalent to nearly 25 trillion miles. With the propulsion technology currently at our disposal, a spacecraft would take tens of thousands of years to cover this immense distance. To make interstellar missions feasible within a human lifetime, the development of advanced propulsion systems is absolutely critical. These systems would need to propel spacecraft at a significant fraction of light speed, reducing travel time dramatically and allowing for more practical missions. But even once a spacecraft has successfully traversed the vast expanse of space, it would still face a multitude of other obstacles. The journey itself exposes any spacecraft to numerous risks. Cosmic radiation, high-energy particles, and interstellar dust all pose serious threats to both the spacecraft's instruments and any potential human crew. Effective shielding will be necessary to protect delicate equipment and ensure the safety of any astronauts who may embark on such a mission. Furthermore, autonomous systems capable of self-repair and maintenance will be indispensable, as human intervention would be nearly impossible during such an extended journey. Another major hurdle involves the challenges of navigation and communication over such immense distances. Current communication technologies are not designed to function across the light years that separate Earth from Proxima Centauri b. Innovations in deep space communication systems will be required to maintain contact with Earth and transmit valuable data throughout the mission. Without such advancements, ensuring the safety and success of an interstellar mission would be highly problematic. Once a spacecraft reaches Proxima Centauri b, the exploration will not get any easier. The planet's proximity to its parent star could expose it to intense stellar radiation, and its surface conditions may be highly unstable, possibly due to tidal locking. This occurs when one side of the planet always faces the star, creating extreme temperature gradients between the day and night sides. Instruments used to study the planet will need to be exceptionally durable, capable of surviving in these extreme conditions while still gathering crucial data. The challenges of collecting meaningful information will require the development of entirely new technologies and methodologies. In conclusion, the prospect of sending a mission to Proxima Centauri b represents one of the most ambitious endeavors humanity could ever undertake. To succeed, we will need to push the boundaries of space technology to new and unimaginable heights. Only through innovation, determination, and collaboration can we hope to overcome these formidable challenges. The future of interstellar exploration rests on our ability to master the complexities of space travel, shield our spacecraft from cosmic dangers, and communicate over vast distances. As we move into this new era, our quest for knowledge will undoubtedly inspire future generations to dream bigger and reach further than ever before. Kepler 186f stands as one of the most intriguing discoveries in the ever-expanding field of exoplanetary science. Situated in the constellation Cygnus, approximately 500 light-years from Earth, This distant world holds particular significance due to its remarkable combination of Earth-like size and its positioning within the habitable zone of its host star, Kepler 186. Discovered by NASA's Kepler Space Telescope in 2014, Kepler 186f ignited the imagination of astronomers and the public alike, offering a tantalizing glimpse of a world that could potentially support life. What makes Kepler 186f truly exceptional is not just its location within the habitable zone, but also its size. With a radius only about 10% larger than Earth's, this exoplanet stands out as a near-Earth twin. Such a size increases the likelihood that Kepler 186f could have a rocky composition similar to Earth's, rather than being a gas giant like many other exoplanets. This is a key factor in determining whether the planet could sustain life, as smaller rocky planets are more likely to have solid surfaces and conditions that allow for liquid water. The concept of liquid water is essential for life as we know it, making Kepler 186f a prime candidate in the search for habitable exoplanets. Orbiting its star, a red dwarf known as Kepler 186, this exoplanet resides in a delicate sweet spot where temperatures might allow liquid water to exist on its surface. Kepler 186f completes an orbit around its star every 130 days. Although its star is cooler and less luminous than our Sun, it still provides enough warmth to support liquid water given the right atmospheric conditions. The fact that the habitable zone around Kepler 186 is much closer to the star than Earth's habitable zone around the Sun adds another layer of intrigue. This proximity helps maintain a balance that could avoid the extreme temperature swings seen on planets too close or too far from their stars. Kepler 186f orbits a star that is drastically different from our Sun in several critical ways. Kepler 186 is an M-dwarf star, a type of red dwarf that is smaller, cooler, and less luminous than the G-type main sequence star that is our Sun. It has only about half the mass and radius of our Sun. Because red dwarfs emit far less light and heat, the habitable zone around such stars is much closer to the star itself. This smaller, cooler nature of the star leads to important consequences for the planets in its orbit, including Kepler 186f. Moreover, red dwarfs like Kepler 186 have notably long lifespans, potentially lasting billions of years longer than stars like our Sun. This extended lifespan is due to their more efficient burning of fuel at a slower rate. While this long lifespan may allow for a stable environment over an extended period, red dwarfs also exhibit intense stellar activity, particularly in their younger years. These activity bursts, such as frequent and powerful stellar flares, can emit harmful ultraviolet and X-ray radiation, which might strip away or severely damage the atmospheres of orbiting planets. This is a significant challenge for the habitability of any exoplanet, as such radiation could influence the potential for life. Despite these high-energy outbursts, the cooler and smaller Kepler 186 might still offer a relatively stable environment for life over an extended period, making it a fascinating subject of study. The star's stellar activity, while potent, could potentially be buffered by the planet's distance from the star and the possibility of an atmosphere capable of shielding the surface from damaging radiation. Understanding these stellar and planetary dynamics helps astronomers assess the true potential of Kepler 186f as a habitable world. Kepler 186f's discovery was groundbreaking, as it was the first exoplanet found within the habitable zone of its star to possess a size similar to Earth. This milestone has paved the way for further research into the search for Earth-like planets. As astronomers continue to study Kepler 186f and similar exoplanets, the dream of finding a second Earth grows ever closer. Each new discovery in this field brings with it the promise of unlocking the mysteries of our universe and the possibility that somewhere in the vastness of space, another world could support life as we know it. This discovery sparked a surge of excitement within the scientific community, as it suggested that Earth-sized planets within the habitable zones of stars, where conditions could potentially support liquid water, might be far more common than we previously imagined. The significance of Kepler 186f reaches far beyond its individual characteristics. This exoplanet has been instrumental in refining both our understanding of planetary detection methods and the criteria we use to assess a planet's habitability. Kepler 186f, orbiting a red dwarf star, marked a pivotal moment in the search for potentially habitable planets. Its discovery validated the theory that planets of a similar size to Earth could indeed exist in the habitable zone, an area around a star where conditions could allow for liquid water, an essential ingredient for life as we know it. The presence of Kepler 186f proved that planets with Earth-like conditions may not be as rare as once thought. But it wasn't just the planet's discovery that made headlines, it was also the method used to detect it. Kepler 186f's confirmation showcased the power and accuracy of the transit photometry technique. In this method, astronomers observe a star's brightness over time, looking for periodic dips caused by a planet passing or transiting in front of its host star. The subtle dimming of the star's light when Kepler 186f crossed in front of it revealed the presence of the exoplanet, providing crucial evidence of its existence. The discovery of Kepler 186f further catalyzed a growing interest in studying red dwarf stars, which are the most common type of star in our galaxy. These stars have long been seen as potential hosts for habitable planets, but Kepler 186f was one of the first to confirm that such stars could indeed support Earth-sized planets in their habitable zones. This has led astronomers to focus more attention on these relatively small and faint stars in the quest for life beyond our solar system. Moreover, the discovery of Kepler 186f has opened the door for future missions and advanced telescopes designed to find and study even more Earth-like planets. The data gleaned from this exoplanet has underscored the importance of continually improving our observational techniques and broadening the criteria by which we search for new worlds. As technology advances, astronomers hope to identify planets that are even more Earth-like, with conditions that could mirror those on our own planet. Kepler 186f's potential for supporting liquid water, a key factor in determining its habitability, lies in its location within the so-called Goldilocks zone of its star. This is the region where a planet's distance from its host star allows for temperatures that are neither too hot nor too cold, creating the perfect conditions for water to exist in liquid form. For Kepler 186f, this zone is a crucial factor in the ongoing debate about whether it could support life. Kepler 186f's discovery did not happen overnight. It was the result of meticulous and continuous observations by NASA's Kepler Space Telescope, which employed the transit photometry method to detect exoplanets. By observing the brightness of stars and looking for subtle fluctuations in light, Kepler was able to spot the tiny dips in brightness caused by planets like Kepler 186f passing in front of their stars. In the case of Kepler 186f, these dips were incredibly faint yet consistent, allowing astronomers to detect the planet and confirm its existence. But confirming the presence of a planet is no simple task. The data collected by Kepler had to be carefully analyzed to eliminate any other possible explanations for the light changes, such as stellar activity or background noise. It took multiple transits over time to confirm the periodicity of these light dips, ensuring that they were indeed caused by an orbiting planet. Once the periodicity was established, astronomers could calculate the planet's size, orbital period, and distance from its host star. Kepler 186f was found to be about 10% larger than Earth, with an orbit of around 130 days. This groundbreaking discovery also required further detailed observational data and sophisticated modeling to estimate the planet's precise size, orbital characteristics, and composition. Once these parameters were confirmed, Kepler 186f was officially recognized as one of the most promising exoplanets in the search for life-supporting worlds. Kepler 186f's confirmation marked a major achievement for the Kepler mission and the field of exoplanet research. It demonstrated that Earth-sized planets could exist in habitable zones around their stars, expanding our understanding of where life-supporting conditions might be found beyond our own solar system. This breakthrough has inspired not only scientists, but also the general public, fueling imaginations and raising profound questions about the potential for life elsewhere in the universe. In conclusion, Kepler 186f stands as a testament to human curiosity and ingenuity. It has reshaped our expectations of what exoplanets could look like, reignited the search for habitable worlds, and laid the groundwork for future missions aimed at uncovering even more Earth-like planets. As we continue to improve our detection techniques, the possibility of finding a planet with conditions similar to Earth grows ever more realistic. Kepler 186f's legacy lives on, continuing to inspire and drive forward the quest to answer one of humanity's greatest questions: are we alone in the universe? This zone offers a fascinating glimpse into the possibility that, under the right atmospheric conditions, surface temperatures could support liquid water, a fundamental ingredient for life as we understand it. But even though Kepler 186f lies within this so-called habitable zone, simply being in the right location is not enough. A planet's atmosphere plays a pivotal role in regulating surface conditions and maintaining a stable environment. Without a sufficient atmosphere, a planet could become far too cold, especially on the side facing away from its star if it experiences tidal locking, where one hemisphere is always in darkness. On the other hand, a thicker atmosphere might cause extreme greenhouse effects, raising surface temperatures to uninhabitable levels, much like the scorching conditions seen on Venus. Kepler 186, the star around which Kepler 186f orbits, is a red dwarf, a star known for emitting powerful stellar flares. These flares could strip away or significantly alter the planet's atmosphere over time, potentially jeopardizing its ability to maintain liquid water. Due to Kepler 186f's proximity to its star, its atmospheric retention and surface conditions would be heavily influenced by the star's behavior. While Kepler 186f's location within the habitable zone provides an intriguing possibility for liquid water, the real conditions depend on many factors, such as the planet's atmospheric composition and the activity of its star. Advanced telescopes, which will be capable of analyzing the planet's atmosphere, are essential to better understand whether Kepler 186f and other planets like it have the potential to support life. Further out in space, there's the TRAPPIST-1 system, located around 39 light-years away in the Aquarius constellation. This fascinating system contains 7 known Earth-sized exoplanets orbiting a single ultra-cool dwarf star. What sets this system apart is not only its potential for habitability, but also the close orbits of these planets to their host star, making them prime candidates for studying planetary formation and the possibility of life beyond our solar system. Among these 7 planets, TRAPPIST-1e is especially intriguing, considered one of the most Earth-like of the group. Positioned within the habitable zone of its host star, TRAPPIST-1e presents an ideal environment for liquid water to potentially exist on its surface. The habitable zone refers to the region around a star where conditions might be just right to allow liquid water to exist, a critical factor for life as we know it. TRAPPIST-1e's size and density closely resemble that of Earth, suggesting it has a rocky composition, which is essential for supporting a stable atmosphere and the development of life. What makes TRAPPIST-1e stand out is that it receives a level of stellar radiation and warmth similar to that which Earth receives from the Sun. This balanced exposure minimizes the likelihood of the planet experiencing the extreme conditions typical in planets that are either too close or too far from their central star. The planet's equilibrium temperature, essentially its surface temperature, assuming a perfect balance between the heat it receives and radiates, suggests it may be capable of maintaining liquid water. These factors together make TRAPPIST-1e a prime target for future missions aimed at detecting atmospheric composition, the presence of water, and possibly even signs of life. While current observations of TRAPPIST-1e are still in their preliminary stages, scientists have made educated guesses based on the planet's characteristics, such as its size, density, and location within the habitable zone. TRAPPIST-1e is believed to have an atmosphere conducive to supporting liquid water, assuming it contains the right mix of gases. One of the primary hypotheses is that its atmosphere could be similar to Earth's, rich in nitrogen and oxygen. Such a composition would be essential for maintaining surface pressure that allows liquid water to exist. Greenhouse gases, like carbon dioxide, could also help trap heat, preventing the planet from freezing, despite the dimmer light of its ultra-cool star. But this balance is delicate. Too much greenhouse effect could lead to runaway heating, while too little could result in a frozen world. Another crucial feature is the potential presence of water vapor, as detecting water vapor in the atmosphere would serve as a significant indicator that liquid water might be present on the planet's surface. The more we learn about planets like Kepler 186f and TRAPPIST-1e, the closer we come to answering one of the greatest questions in science. Could there be life beyond Earth? As future missions to these distant worlds progress, they may hold the key to unlocking that mystery. The pursuit of knowledge continues, revealing the extraordinary conditions required for life and the potential for discovering it on exoplanets far from our own. The James Webb Space Telescope and other advanced observatories are paving the way for a revolution in the search for extraterrestrial life. These next-generation instruments are expected to offer unprecedented insights into distant worlds, with TRAPPIST-1e emerging as one of the most fascinating candidates in the quest for signs of life beyond our solar system. Situated within the habitable zone of its ultra-cool star, TRAPPIST-1, this exoplanet is poised to be a focal point of cutting-edge research. What makes TRAPPIST-1e particularly compelling is its location in the so-called Goldilocks zone, where conditions may be just right for liquid water to exist, an essential ingredient for life as we know it. The planet's proximity to its star, coupled with its Earth-like size and composition, suggests that it could harbor a rocky surface. This characteristic is vital for the presence of an atmosphere and the cycling of nutrients, two key factors that could support life. A rocky planet like TRAPPIST-1e could retain an atmosphere strong enough to protect life forms from harmful stellar radiation, while maintaining stable conditions necessary for liquid water to persist on its surface. In addition to its habitability, TRAPPIST-1e is tidally locked, meaning that one hemisphere constantly faces the star while the other remains in perpetual darkness. This unique feature creates extreme temperature gradients between the day and night sides. However, the planet's atmosphere could play a crucial role in regulating heat distribution across the surface. Scientists will need to study its atmospheric dynamics closely to understand how it might stabilize the planet's climate, making it more suitable for life. The ability of the atmosphere to circulate heat effectively between the two hemispheres could be key to sustaining habitable conditions over long periods. At just 39 light-years away, the TRAPPIST-1 system is relatively close by cosmic standards, making it an ideal target for detailed study with current and upcoming telescopes. Instruments like the James Webb Space Telescope will be able to scrutinize the planet's atmosphere, looking for biomarkers such as water vapor, methane, and oxygen, gases that could point to the presence of biological activity. Researchers are particularly eager to identify these chemical indicators, which could help confirm whether life ever existed, or could potentially exist on this distant world. TRAPPIST-1e's relatively stable host star is another advantage for potential habitability. As an ultra-cool dwarf, TRAPPIST-1 is far less volatile than other types of stars, emitting a steady flow of energy over long periods. While the star does experience occasional flares, its lower overall energy output reduces the risk of harmful radiation spikes. This makes the planet's surface more conducive to life, without the constant threat of sterilizing radiation that larger, more active stars could impose. The planet orbits its star at a distance of just 0.028 astronomical units, AU, much closer than Earth's 1 AU from the Sun. This proximity means that TRAPPIST-1e likely experiences extreme conditions compared to Earth, with temperatures that could fluctuate drastically between the day and night sides. Despite these challenges, scientists believe the planet's atmosphere might have the capability to balance these extremes, supporting a more temperate climate. TRAPPIST-1e's closeness to its host star also allows for more frequent and detailed observations, which could uncover new insights into how planets in such close proximity to their stars can maintain stable environments for long-term habitability. In conclusion, TRAPPIST-1e stands as one of the most promising exoplanets in the search for extraterrestrial life. Its position within the habitable zone, Earth-like characteristics, and the potential for detailed observation make it a prime candidate for future studies. As scientists continue to study the planet's atmosphere and physical properties, they may soon uncover the secrets to its potential for supporting life, offering a glimpse into what may lie beyond our own planet. TRAPPIST-1, an ultra-cool dwarf star, is strikingly different from our Sun in many ways. Much smaller and cooler, TRAPPIST-1 emits far less light and heat. Because of its significantly lower temperature and luminosity, the habitable zone around this star is considerably closer than the one we have around our Sun. This means that while Earth orbits the Sun at a comfortable distance, allowing the planet to receive just the right amount of energy to sustain liquid water and life, TRAPPIST-1e, one of the planets orbiting TRAPPIST-1, must orbit much closer to its parent star to achieve similar energy levels. However, this proximity has an intriguing consequence. TRAPPIST-1e completes a full orbit around its star in just 6 Earth days. This rapid orbit, despite the planet's closeness to the star, results in a fascinating contrast. The star's low luminosity means that the energy and radiation received by TRAPPIST-1e are actually comparable to what Earth receives from the Sun. However, this tight orbit also raises the possibility of tidal locking. In this scenario, one side of TRAPPIST-1e would permanently face the star, while the other side remains in darkness, creating 2 drastically different climates, a scorching day side and a freezing night side. The question of whether TRAPPIST-1e could regulate these extremes through atmospheric circulation remains a tantalizing subject for further research and exploration. The discovery of TRAPPIST-1e, a potentially habitable exoplanet within the TRAPPIST-1 system, marks a monumental achievement in modern astronomy. It was made possible through a perfect synergy of cutting-edge technologies and methodologies. The primary instrument responsible for this discovery was the Transiting Planets and Planetal Small Telescope, TRAPPIST, located in the mountains of Chile. This small but powerful observatory employs the transit method, carefully tracking the minute dimming of a star's light as planets pass in front of it, revealing their existence. The findings from TRAPPIST were then complemented and further enhanced by the Spitzer Space Telescope. With its ability to observe in infrared, Spitzer enabled astronomers to study the faint variations in light with much greater precision. This allowed scientists to better understand the composition of the planets, their orbits, and their potential for habitability. In addition to these telescopes, the collaboration of advanced data processing algorithms played a vital role. Sophisticated software was used to analyze vast amounts of data, sifting through periodic dips in the star's light to confirm the presence of the planets. The high-accuracy radial velocity planet searcher, HARPS, also played a crucial role in verifying TRAPPIST-1e's existence. HARPS is known for its extreme precision in measuring the subtle shifts in a star's light, which are indicative of orbiting planets. With its help, astronomers were able to confirm the planet's mass and orbital parameters. This collaboration between multiple observatories worldwide, alongside numerical modeling and simulations, has propelled our understanding of the TRAPPIST-1 system. Together, these technological advancements represent a giant leap forward in our ability to detect, study, and understand distant exoplanets. This groundbreaking work brings us one step closer to answering one of humanity's oldest and most profound questions. Are we alone in the universe? With every new discovery, our understanding of the cosmos expands, unveiling the mysteries of distant worlds that may one day hold the key to life beyond our own planet. The potential for life on exoplanets like TRAPPIST-1e continues to inspire hope and curiosity in the hearts of scientists and dreamers alike. In October 1995, the astronomical world was forever changed with the announcement of the groundbreaking discovery of 51 Pegasi b by astronomers Michel Mayor and Didier Queloz. Located approximately 50 light-years away in the Pegasus constellation, this marked the first confirmed detection of an exoplanet orbiting a sun-like star. This discovery did more than just open a new chapter in astrophysics. It sparked a full-fledged revolution in our understanding of planetary systems, offering a glimpse into the vast possibilities of alien worlds. Before this monumental breakthrough, exoplanet discoveries had been confined to pulsar planets, planets orbiting the dense remnants of dead stars. These pulsar planets had limited significance, offering little insight into the formation and dynamics of planetary systems akin to our own. The discovery of 51 Pegasi b, however, shattered these constraints. It revealed the presence of planets orbiting stars similar to the Sun, by fundamentally altering our perspective on the cosmos and igniting a global rush to search for other Earth-like worlds. Dubbed a hot Jupiter, 51 Pegasi b defied existing theories about planetary formation and behavior. It orbits its star in a blistering 4-day period, an incredibly short orbital period when compared to the Earth's 365-day journey around the Sun. This extreme proximity at just 0.05 astronomical units AU from its host star was nothing short of revolutionary. Prior models suggested that gas giants, like Jupiter, should only form at greater distances from their stars. But 51 Pegasi b's close orbit challenged this assumption, prompting the scientific community to rethink planetary migration models. The discovery ignited new theories as about how planetary systems evolve, incorporating the idea that planets could migrate inward toward their stars over time. Moreover, the discovery of 51 Pegasi b demonstrated the power of the radial velocity method, a technique that detects exoplanets by observing the tiny wobbles they induce in their host stars due to gravitational interactions. The success of this method in identifying 51 Pegasi b paved the way for the discovery of thousands of other exoplanets, providing a new avenue for exploration and enriching our understanding of the universe. This method, alongside other advancements in technology, transformed the field of astronomy, revealing an astonishing diversity of planets, some far beyond our imagination. 51 Pegasi b's classification as a hot Jupiter comes with its own set of defining characteristics. Like Jupiter, it is a gas giant, sharing similar size and composition. However, what sets it apart and earns it the hot moniker is its extreme proximity to its star. While Jupiter resides about 5 AU from the Sun, 51 Pegasi b orbits at a mere 0.05 AU, a mere 1/12 of the distance from Earth to the Sun. As a result, temperatures on 51 Pegasi b are searing, estimated to reach 1,000 degrees Celsius, far hotter than the much cooler temperatures found on Jupiter. Additionally, the rapid orbital period of 51 Pegasi b is a significant factor in its classification. Completing a full orbit in just over 4 Earth days, the planet experiences a gravitational pull from its star that is far stronger than anything we see in our solar system. This intense pull, in combination with the planet's close proximity to its star, exposes 51 Pegasi b to extreme stellar radiation. Such conditions often result in tidal locking, where one hemisphere of the planet constantly faces its star, leaving the other hemisphere in eternal darkness. The scenario on 51 Pegasi b is a stark contrast to our own Earth, where day and night shift regularly due to our axial tilt and orbit. For 51 Pegasi b, one side is perpetually scorched while the other remains in a freezing night, making it a fascinating yet extreme example of a hot Jupiter. The discovery of 51 Pegasi b is far more than just an astronomical milestone. It is a story of how human curiosity and technological advancement converge to expand our understanding of the universe. Its implications stretch far beyond our own solar system, hinting at the possibility of countless other alien worlds, many of which we may one day visit or explore. The journey of discovery that began with 51 Pegasi b continues to evolve, with each new exoplanet contributing to the rich tapestry of our cosmic knowledge, drawing us ever closer to understanding our place in the vast expanse of space. The discovery of 51 Pegasi b, the first exoplanet found orbiting a sun-like star, marks a pivotal moment in the field of astronomy. Its extreme atmospheric conditions, unique characteristics, and unexpected proximity to its host star have challenged long-standing assumptions about planetary systems. The revelation of 51 Pegasi b as a hot Jupiter, a gas giant orbiting very close to its star, has opened a new chapter in our understanding of how planets can form, evolve, and behave in ways we once thought impossible. What makes this discovery particularly fascinating is how it directly confronted conventional theories of planetary formation. Before 51 Pegasi b, scientists believed that gas giants like Jupiter could only form in the outer reaches of planetary systems, far from their stars. Our own solar system, with its gas giants orbiting at vast distances, reinforced this model. But 51 Pegasi b, orbiting at just 0.05 astronomical units from its star, shattered that notion. Here was a gas giant existing in extreme proximity to its star, in conditions once considered too hostile for such planets to survive. This revelation sparked a seismic shift in our understanding, pushing scientists to rethink how planets, particularly gas giants, migrate inward during the formation process. This insight led to the development of more sophisticated theories, suggesting that gas giants can indeed migrate from their original positions toward their stars. Such migration is influenced by gravitational interactions with surrounding bodies and the protoplanetary disk. With this new understanding, astronomers were better equipped to explain the existence of hot Jupiters and other unusual exoplanets that defied previous models. Furthermore, the discovery of 51 Pegasi b was not just a breakthrough in planetary science, but also in observational techniques. The use of the radial velocity method to detect this planet, measuring the slight wobbles in a star's motion caused by the gravitational pull of an orbiting planet, was a game changer. Before this, detecting exoplanets was a difficult, imprecise task. The success of this technique, however, validated its effectiveness, and it quickly became the cornerstone of exoplanet hunting. This breakthrough led to a rapid increase in the discovery of exoplanets, unveiling thousands of new worlds with diverse characteristics, from gas giants to rocky planets, and even entirely new classes like super-Earths and mini-Neptunes. But the significance of 51 Pegasi b doesn't stop with its discovery. It also dramatically expanded the known diversity of planetary systems. Once thought to be a universal blueprint, our solar system's structure now seems just one of many possible arrangements. The discovery of 51 Pegasi b proved that planetary systems come in a mind-boggling array of configurations, each with its own unique conditions and dynamics. This realization has driven advances in telescope technology as well as ambitious space missions aimed at studying exoplanets in greater detail, fueling a broader quest to understand the complexity of the universe. The atmospheric conditions on 51 Pegasi b are as extreme as the planet's location. Due to its close proximity to its star, temperatures on the planet can soar to over 1,000 degrees Celsius. This intense heat creates a radically different atmosphere compared to cooler planets, with the likely presence of ionized metals and exotic chemical reactions. Observations from space telescopes suggest high concentrations of elements like sodium and potassium in the atmosphere, substances that are easier to detect in such high-temperature environments. Adding to the intrigue is the possibility that 51 Pegasi b is tidally locked, meaning one side of the planet always faces the star, while the other is in perpetual darkness. This stark temperature contrast between the day and night sides could generate supersonic winds, stirring up the planet's atmosphere in unpredictable ways. These winds would redistribute heat across the planet, influencing weather patterns in ways scientists are only beginning to understand. The sheer scale and complexity of these phenomena make 51 Pegasi b an unparalleled laboratory for studying extreme planetary environments. In the years since its discovery, 51 Pegasi b has inspired countless studies and fueled a reimagining of the types of planets that can exist beyond our solar system. As technology advances and our understanding deepens, the fascinating weather dynamics and atmospheric peculiarities of planets like 51 Pegasi b will continue to challenge our expectations and expand the horizons of astronomical research. The atmosphere of exoplanets, particularly under extreme conditions, reveals a wealth of information about atmospheric physics and heat transfer. Observations from powerful instruments, such as the Hubble Space Telescope spectrograph, have refined our understanding of the atmospheric properties of distant worlds. These observations highlight the surprising complexity and variety found in exoplanet atmospheres, underscoring their divergence from the planets in our own solar system. When comparing 51 Pegasi b to Jupiter, the differences and similarities between these two gas giants become strikingly evident. Both planets share a similar mass and radius, with 51 Pegasi b being roughly half the mass of Jupiter. Yet, the most apparent divergence lies in their orbits. While Jupiter follows an orbit at a comfortable 5 astronomical units AU from the Sun, 51 Pegasi b orbits its host star, 51 Pegasi, at a scorching distance of only 0.05 AU. This close proximity results in an astonishingly brief orbital period of just over 4 Earth days. Contrast this with Jupiter's leisurely 12-year orbit. This drastic difference in distance directly influences the temperature of each planet. While Jupiter maintains an average cloud top temperature of a frigid -145 degrees Celsius, 51 Pegasi b, a hot Jupiter, experiences searing atmospheric temperatures that soar to around 1,000 degrees Celsius. The extreme heat present on 51 Pegasi b profoundly impacts its atmosphere. It leads to the presence of exotic chemicals, ionized metals, and clouds of high-altitude gas, phenomena not seen on Jupiter, which is far colder. Additionally, the potential tidal locking of 51 Pegasi b, where one side constantly faces its star, introduces conditions that give rise to intense weather systems, including supersonic winds. These winds redistribute heat across the planet's atmosphere, further enhancing the extreme weather patterns. Despite the vast differences in their environments, both planets share a core similarity. They are gas giants, lacking solid surfaces and composed mostly of hydrogen and helium. The substantial gravitational forces they exert on their respective systems further cement their status as dominant forces in their star systems. Comparing these planets underscores the stunning diversity of planetary systems in the universe, highlighting the broad spectrum of environments in which gas giants can thrive, from the cold, distant reaches of our solar system to the blistering close orbits of stars in other parts of the galaxy. Kepler 22b, on the other hand, offers a strikingly different perspective on exoplanetary systems, particularly due to its location in the habitable zone of its star. This region, often referred to as the Goldilocks zone, is neither too hot nor too cold, providing the ideal conditions for liquid water to exist on a planet's surface, one of the key ingredients for life as we know it. Discovered by NASA's Kepler Space Telescope, Kepler 22b orbits its star, Kepler 22, at a distance of approximately 0.85 astronomical units, placing it comfortably within this habitable zone. What makes this planet particularly exciting is that its host star closely resembles our own Sun, though slightly smaller and cooler. This similarity results in a stable and consistent energy output, crucial for maintaining the favorable conditions that could support water-based life. Kepler 22b is also notable for its size, which is about 2.5 times the radius of Earth. This places it in the category of super-Earths, a class of exoplanets that are larger than Earth but much smaller than gas giants like Neptune or Uranus. The size of Kepler 22b raises intriguing questions about its composition. Could it be an Earth-like rocky planet with a substantial atmosphere, or might it be more like a mini Neptune with a thick, gaseous envelope? While scientists are still working to determine its exact makeup, the planet's estimated equilibrium temperature of around 22 degrees Celsius brings it tantalizingly close to the conditions required for human habitability. This discovery has captivated researchers, as it opens up the possibility of finding a world that could harbor life, whether microbial or potentially more complex, in a stellar system not unlike our own. Despite its larger size compared to Earth, Kepler 22b's relatively stable environment and proximity to its star make it an exciting candidate for future studies in the search for life beyond our solar system. Kepler 22b is a fascinating and mysterious planet that continues to intrigue astronomers, especially due to its substantial size and potential implications for habitability. This size difference implies that Kepler 22b has a much greater volume and possibly a higher mass, likely resulting in a stronger gravitational pull at its surface. However, its exact mass remains uncertain, as the discovery of this planet was primarily based on the transit method. This method provides valuable information about the planet's size, but leaves its mass shrouded in mystery. The larger size of Kepler 22b presents profound implications for what we might find on its surface. If the planet shares a similar rocky composition to Earth, its greater volume could mean a more substantial atmosphere. Additionally, this could result in dynamic geological activity, potentially caused by intense internal pressures. On the other hand, Kepler 22b could also be surrounded by a thick gaseous envelope, akin to a mini Neptune, which would place an entirely different emphasis on understanding the planet's atmospheric composition and structure. Unlike Earth's thinner atmosphere and smaller size, Kepler-22b's size would require a deeper exploration of its surface conditions to truly grasp the planet's potential for sustaining life. One of the most intriguing aspects of Kepler-22b is its potential for habitability. Positioned within the habitable zone of its star, Kepler-22b sits in a region where conditions could be suitable for liquid water, a fundamental ingredient for life as we know it. Its equilibrium temperature, estimated to be around 22 degrees Celsius, further strengthens the possibility of a temperate climate that could support liquid water, assuming it has an Earth-like atmosphere. This could offer a glimpse into what life might look like on a planet that isn't too dissimilar from our own. However, the true potential for habitability is dependent on several uncertain factors. Kepler-22b's size, approximately 5 times the radius of Earth, suggests a stronger gravitational pull, which could affect its ability to retain an atmosphere and sustain surface conditions that would be conducive to life. If Kepler-22b is rocky and possesses a significant atmosphere, it could maintain stable weather patterns, perhaps even with a climate system capable of supporting life. Conversely, if the planet has a thick, Neptune-like gaseous envelope, it might not be suitable for life as we understand it. High pressures and hostile environmental conditions could render the surface uninhabitable for most forms of life. Another key element to understanding Kepler-22b's habitability is its atmospheric composition. A dense atmosphere rich in greenhouse gases such as carbon dioxide could trigger a runaway greenhouse effect, resulting in surface temperatures too high to support life. Alternatively, if the planet's atmosphere is well balanced, containing a mix of gases like nitrogen, oxygen, and carbon dioxide, it could significantly improve the chances for habitability. Until advanced telescopes like the James Webb Space Telescope can provide more detailed observations, the exact nature of Kepler-22b's atmosphere remains a tantalizing mystery. Despite the uncertainties surrounding Kepler-22b, it stands as a prime candidate in the search for extraterrestrial life. The curiosity it sparks and the scientific endeavors it drives are advancing our understanding of planets beyond our solar system. As we continue to investigate this fascinating world, we inch closer to unlocking its secrets that could potentially change our understanding of life in the universe forever. Kepler-22b, an intriguing exoplanet, was first detected using the highly effective transit method, an innovative technique pioneered by NASA's Kepler Space Telescope. This method was specifically designed to uncover Earth-like planets orbiting distant stars. The process involves observing a star's brightness over an extended period, searching for periodic dimming events. These dimming events occur when a planet crosses in front of its host star, blocking a small portion of the starlight, an event known as a transit. The slight reduction in light intensity caused by the planet is minuscule but measurable, and this subtle dip allows astronomers to gather essential data about the planet's characteristics. The discovery of Kepler-22b began when the Kepler telescope, over the course of 3 years, captured multiple instances of dimming from the star Kepler-22. These dimming events, occurring at regular intervals, matched the orbital period of the suspected planet, which was approximately 290 days. However, this initial signal was not enough to confirm the presence of the planet. To rule out potential false positives, such as binary star systems or star variability, follow-up observations were crucial. Ground-based telescopes and additional measurements were employed to gather more data. Using sophisticated algorithms and analyzing the consistency of the dimming, astronomers could refine the planet's size and orbital parameters. Through these advanced techniques, they confirmed the existence of Kepler-22b. Kepler-22b's confirmation was a pivotal moment in exoplanet research, as it marked one of the first discoveries of a super-Earth located within the habitable zone of its star, an area where liquid water could exist. The planet's position in the habitable zone underscored the potential for life beyond our solar system. This discovery not only demonstrated the capabilities of the Kepler Space Telescope and the transit method, but also spurred optimism in the search for Earth-like planets. Kepler-22b's significance went beyond its potential for supporting life. It also served as a benchmark for future missions in the search for habitable worlds. The discovery of Kepler 22b fueled further interest in the study of super-Earths, planets larger than Earth but smaller than Neptune. With a radius about 2.5 times that of Earth, Kepler 22b challenged existing models of planet formation and habitability. It forced scientists to reconsider the diversity of planetary types and what conditions might support life. Researchers started to broaden their definitions of habitability, taking into account factors such as atmospheric composition, geothermal activity, and the possibility of liquid water. These investigations led to advancements in atmospheric modeling, enabling scientists to refine the criteria for what makes a planet truly habitable. Moreover, Kepler 22b's discovery highlighted the importance of using a multi-method approach in confirming exoplanets. While the transit method provided the initial clue, additional observations were essential to verify the planet's characteristics and ensure it wasn't a false alarm. This process of cross-referencing and collaboration set a valuable precedent for future exoplanet research. It emphasized the necessity of using diverse observational platforms and techniques to gain a comprehensive understanding of distant worlds. In the grander scheme, Kepler 22b has played an instrumental role in expanding our understanding of exoplanets. Its discovery not only broadened the potential locations for habitable worlds, but also refined the scientific methods used to explore them. The lessons learned from this discovery continue to shape the tools and strategies employed in the search for life beyond Earth, paving the way for future discoveries that might one day reveal the presence of life on distant planets. Earth-like exoplanets continue to captivate our imagination, and one of the most intriguing and controversial examples is Gliese 581g. Discovered in 2010 by astronomers Stephen Vogt and R. Paul Butler, this exoplanet sparked widespread excitement due to its location in the habitable zone of the red dwarf star Gliese 581. The initial announcement claimed that Gliese 581g, orbiting just 20 light-years away in the Libra constellation, could be the first truly Earth-like planet found outside our solar system, capable of harboring life. At the heart of the excitement was the potential for liquid water, a critical ingredient for life as we know it. With a mass roughly 3 to 4 times that of Earth, Gliese 581g appeared to be in the Goldilocks zone, the area around a star where conditions might be just right for liquid water to exist. However, the initial enthusiasm was tempered by mounting skepticism as further analysis raised doubts about the planet's existence. The problem stemmed from the method used to detect the planet: radial velocity. This technique measures the wobble in a star's motion caused by the gravitational pull of an orbiting planet. Yet, the signals associated with Gliese 581g were on the edge of detection capabilities and sometimes indistinguishable from stellar activity noise or data processing errors. Some astronomers speculated that what was originally thought to be a planet might have been a false positive, an illusion created by stellar variability rather than a true planetary signal. This debate underscores the inherent complexities of detecting exoplanets, particularly those orbiting low-mass stars like red dwarfs, which are notorious for their turbulent activity that can mimic the faint signals of orbiting planets. As the controversy unfolded, the scientific community was forced to confront the challenges of distinguishing real planetary signals from the natural noise produced by stars themselves. In a sense, this episode has become a case study in the evolution of exoplanet detection techniques, highlighting the importance of rigorous verification and the role of skepticism in advancing scientific understanding. Despite the doubts surrounding its existence, the initial discovery of Gliese 581g had a profound impact on the field of exoplanet research. It prompted a renewed focus on red dwarf systems and their potential to harbor habitable planets. The debate also underscored the need for more advanced observational technologies that could better separate the signal of an exoplanet from the background noise of its parent star. Even though Gliese 581g's status remains uncertain, the controversy it sparked has led to improvements in detection methods and has provided valuable lessons for future exoplanet hunts. As we shift our focus back to the potential habitability of Gliese 581g, Its orbit within the habitable zone of Gliese 581 presents a unique set of challenges. Located much closer to its parent star than Earth is to the Sun, because red dwarfs are cooler and less luminous, the planet's proximity suggests that it could, theoretically, possess the right conditions for liquid water. However, life on such a planet might not be as idyllic as it sounds. Red dwarfs, particularly in their younger stages, are notorious for their powerful stellar flares and intense radiation, which could strip away the planet's atmosphere or create an inhospitable surface environment. Nonetheless, there's hope. If Gliese 581g has a thick atmosphere or a strong magnetic field, it may be able to protect itself from the worst of these stellar flares. Such a shield could potentially mitigate the effects of the harsh radiation that would otherwise make the surface uninhabitable. Additionally, Gliese 581g's potential to be tidally locked, a condition where one side of the planet perpetually faces its star while the other remains in darkness, adds another layer of complexity. The constant exposure to the star on one side would result in extreme temperatures, while the dark side could become bitterly cold. This could create violent atmospheric circulation patterns as heat attempts to redistribute from the day side to the night side. Interestingly, the boundary between the day and night sides, the Terminator line, could offer a more temperate and stable climate. In this twilight zone, temperatures might be moderate enough to support liquid water, creating a unique environment that could, in theory, support life. This region, located in the narrow strip between the scorching heat of perpetual day and the freezing cold of eternal night, could be the most promising area for life on Gliese 581g. While the controversy over its existence remains unresolved, the potential for Gliese 581g to support life in its unique environment continues to inspire further study. Its discovery and the ensuing debate have played a crucial role in refining the methods we use to search for habitable planets, ensuring that future discoveries will be made with greater precision and understanding. Whether or not Gliese 581g is truly out there, its story has already left an indelible mark on the field of exoplanet research. Pushing the boundaries of what we know about planets beyond our solar system and our ongoing search for life elsewhere in the cosmos. If the atmospheric conditions are right, this could create a narrow habitable band around the planet, a zone where, if life exists, it might find a suitable refuge. This intriguing possibility stems from the delicate balance between a planet's atmosphere and its orbit. But the story doesn't end there. Atmospheric dynamics may also help equalize temperatures across the entire planet, potentially fostering globally habitable conditions, not just within the traditional Goldilocks zone, or the so-called twilight zone. However, understanding the precise impact of Gliese 581g's orbit on its climate is far from straightforward. Factors like the composition of the atmosphere, its thickness, and the presence of water or greenhouse gases play a pivotal role in shaping the planet's climate. This complexity means that advanced modeling and the deployment of next-generation telescopes will be essential in the coming years to unveil the true habitability of Gliese 581g. These future observational technologies will provide crucial insights into how this distant planet's atmosphere and climate interact, helping scientists assess whether it might indeed support life. Gliese 581g, located in the Libra constellation, has long been a subject of fascination for scientists studying planetary climates and the potential for life beyond Earth. Its discovery revolutionized our understanding of exoplanets, particularly those that might harbor life. But like many astronomical discoveries, Gliese 581g is shrouded in uncertainty and complexity. While the planet's potential for supporting life is exciting, the complexities that surround its atmospheric conditions and climate dynamics make it an ongoing mystery, an ever-evolving subject of study. The discovery of Gliese 581g, initially hailed as a groundbreaking moment in the search for habitable exoplanets, primarily utilized the radial velocity method, also known as Doppler spectroscopy. This technique, which has become a cornerstone of exoplanet detection, involves detecting the subtle wobbles in a star's motion caused by the gravitational pull of an orbiting planet. As a planet orbits its star, it exerts a gravitational force that causes the star to move in a tiny orbit of its own. This motion results in periodic shifts in the star's spectral lines due to the Doppler effect, an observable phenomenon where light shifts toward the blue end of the spectrum as the star moves toward Earth, blue shift, and toward the red end as it moves away, red shift. By meticulously measuring these shifts, astronomers can infer the presence of a planet, its mass, and its orbital characteristics. In the case of Gliese 581G, a team of astronomers led by Stephen Vogt and R. Paul Butler conducted long-term monitoring of the star Gliese 581 using high-resolution spectrographs like the High-Accuracy Radial Velocity Planet Searcher, HARPS, at the European Southern Observatory's La Silla Observatory in Chile, and the HIRES instrument at the Keck Observatory in Hawaii. These instruments are among the most sensitive in the world, designed to detect the minute radial velocity variations indicative of low-mass planets. For years, the team observed Gliese 5I81, collecting an extensive dataset to identify periodic signals that could be attributed to orbiting planets. Their analysis suggested the existence of a planet with a mass roughly 3 to 4 times that of Earth, orbiting within the star's habitable zone. But this wasn't a simple confirmation. The data had to undergo complex processing and statistical analysis to separate the planetary signals from stellar activity and noise, an incredibly challenging task in the field of exoplanet research. In 2010, the world learned of the discovery of Gliese 581G, based on this analysis of periodic wobbles in the star's motion. However, subsequent observations have sparked heated debates about the planet's existence. Some researchers suggest that the signal attributed to Gliese 581G could be a false positive, possibly caused by stellar activity or data processing artifacts. Despite these controversies, the radial velocity method continues to be a powerful tool for identifying exoplanets, especially those in nearby star systems, and remains central to the quest to find habitable worlds beyond our solar system. The ongoing debate about the existence of Gliese 581G highlights the challenges faced by astronomers in their pursuit of understanding distant worlds. With strong arguments both for and against the planet's existence, the question remains open. Some maintain that the initial data analysis by Vogt and Butler offers compelling evidence for Gliese 581G's existence, while others call for caution, urging further research to confirm or refute the planet's role in the search for life beyond Earth. Gliese 581G's story is far from over, and as new data and improved technologies emerge, its mystery continues to captivate scientists and the public alike. The quest for understanding this enigmatic planet and whether it could host life is far from settled, but one thing is clear. Gliese 581 Dream stands as a symbol of the incredible complexity and potential of exoplanet research. They identified periodic signals in the star Gliese 581, which hinted at the presence of a planet with a mass 3 to 4 times that of Earth. This planet, they speculated, might be located within the star's habitable zone, a region where liquid water could potentially exist, an essential ingredient for life as we understand it. The initial measurements painted a picture of a planet with an orbital period of around 37 days, which seemed to match the expected gravitational influence such a planet would have on its host star. Adding to the allure of Gliese 581G's discovery, its position in the habitable zone of its red dwarf star was particularly compelling. The habitable zone is critical because it's the region where temperatures could allow liquid water to persist on the planet's surface. Theoretical models suggested that, if confirmed, Gliese 581G might have conditions conducive to supporting life, potentially a major breakthrough in the search for extraterrestrial life. This theory was further bolstered by the planet's size, which seemed to suggest a structure capable of retaining an atmosphere, a vital factor for sustaining life. But despite the initial excitement, not everyone was convinced about Gliese 581G's existence. Critics raised several points of contention. One of the main arguments was the reliability of the data, especially in light of subsequent studies that reanalyzed the original signals. These studies suggested that the signals initially attributed to the planet could actually be artifacts of stellar activity or noise within the star's spectral data. Red dwarfs like Gliese 581 are known for their magnetic activity, which can create false positive signals in radial velocity measurements, an issue that had potentially confounded earlier findings. To further complicate matters, multiple independent research teams tried to verify Gliese 581g's existence but failed to produce consistent evidence. Studies using high-resolution spectrographs like those from HARPS and the Hires instrument at Keck Observatory either failed to detect the planet or attributed the observed signals to stellar dynamics rather than a planetary companion. Critics also questioned the statistical methods used in the initial discovery. They argued that the algorithms employed to filter the data might not have adequately accounted for the complexities of the star's activity, leading to overstatements about the presence of the planet. This ongoing debate underscores the challenges of exoplanet detection, particularly when studying active stars. While the initial discovery sparked hope and optimism about finding a potentially habitable planet, the controversies surrounding it also highlight the necessity for rigorous validation using a range of observational techniques. The case of Gliese 581g illustrates just how difficult it is to confirm the existence of exoplanets, especially those orbiting stars with significant magnetic activity. Gliese 581g, often referred to as a second Earth, orbits the red dwarf star Gliese 581, situated approximately 20 light-years away in the constellation Libra. Its most intriguing feature is its location within the star's habitable zone. If the planet exists, it would occupy the sweet spot where conditions might allow for liquid water to exist, making it a prime candidate in the search for extraterrestrial life. The planet's estimated size and mass, 3 to 4 times that of Earth, suggest it would have enough gravity to hold onto an atmosphere, which is essential for regulating temperature and shielding the surface from harmful solar radiation. Further enhancing Gliese 581g's appeal is its orbital period, which could result in one side of the planet being bathed in perpetual daylight while the other remains in endless night. This creates a twilight zone that might harbor relatively stable temperatures, conditions that could be more hospitable to life than extremes of heat or cold. Though there's no direct evidence of life on Gliese 581g, and we remain uncertain about its atmosphere and surface conditions, the scientific community's continued interest in this distant world highlights its potential significance. Beyond Gliese 581g, the universe offers a fascinating array of exoplanets, each more mysterious than the last. One such planet is HD 18973b, located about 63 light-years from Earth in the constellation Vulpecula. This gas giant is known for its extreme and chaotic weather patterns, making it one of the most volatile exoplanets discovered to date. The planet's proximity to its parent star results in scorching temperatures, averaging around 1,000 degrees Celsius on its day side. This intense heat gives rise to some of the most extreme weather ever recorded. What makes HD 18973b particularly captivating are its winds, which can reach speeds of up to 5,400 miles per hour, more than 20 times faster than the strongest hurricanes on Earth. These hyperspeed winds whip across the planet's surface, redistributing heat from the blistering day side to the cooler night side, creating a planet-wide storm that never ceases. These winds are just one example of the extraordinary and often violent weather systems that exist on exoplanets far beyond our solar system. They remind us of the dynamic nature of distant worlds, constantly challenging our understanding of what conditions might support life in the universe. Furthermore, HD 18973b is a planet that stands as a testament to the extremes of nature. Imagine a world where the weather itself seems straight out of a nightmare, rains of molten glass falling from the sky. This vision may sound surreal, but some scientists theorize that this is exactly what happens on HD 18973b, a world located roughly 63 light-years away from Earth. The planet's atmosphere, filled with silicate particles, condenses at staggering altitudes, only to be whipped away by winds moving at terrifying speeds. The result? A sky filled with blistering molten glass, a phenomenon unlike anything witnessed on our home planet. Such intense weather is made possible by two main factors: the variety of atmospheric particles and the planet's tidal locking to its star. Just as the moon always shows the same face to Earth, HD 18973b is locked in a tight embrace with its star, always presenting one side to the heat and light and the other side to the cold, dark void of space. The constant exposure to this unrelenting heat means the daytime side of the planet experiences temperatures soaring to a searing 1,000 degrees Celsius, 1,800 degrees Fahrenheit. These extreme temperatures and intense winds combine to create some of the most violent weather systems observed in any exoplanet, making this distant world an exceptional case study in the variety of climatic conditions that exist in our universe. This captivating discovery was made possible by the transit technique, a method that has revolutionized our understanding of exoplanets. It works by observing the slight dip in a star's brightness as a planet crosses in front of it, blocking a fraction of the light. When astronomers noticed this dimming in the light curve of HD 189733, it revealed the presence of this strange alien world. The transit technique doesn't just reveal the existence of a planet. It also allows scientists to estimate its size, orbital parameters, and other key characteristics. In the case of HD 189733b, the technique allowed the team led by French astronomer François Bouchy in 2005 to confirm the presence of the planet and gather important data about its size, orbit, and later, its atmospheric properties. Subsequent observations made with advanced instruments like the Hubble Space Telescope and the Spitzer Space Telescope have helped deepen our understanding of HD 189733b's extreme weather conditions. These instruments have provided crucial insights into the planet's atmosphere and further confirm the hypothesis of molten glass rain whipped around by hurricane-like winds. The rapid pace of these discoveries shows how the transit method, while initially confirming the planet's existence, has opened the door to an entirely new field of exoplanetary science. HD 189733b is one of the most extreme exoplanets known to us, marked by its proximity to its star, which causes it to experience tidal locking. This creates a planet where one hemisphere is locked in a permanent day, while the other exists in an eternal night. The daytime side, scorched by the relentless heat, reaches temperatures so high that it is almost unfathomable by earthly standards. Meanwhile, the night side, shielded from the star's warmth, is subjected to a chilling, frigid darkness. Adding to the apocalyptic imagery, the winds on HD 189733b are among the fastest ever recorded on a planet, reaching speeds of up to 5,400 miles per hour, almost 7 times the speed of sound. These winds, combined with the intense temperature difference between the day and night sides, contribute to a state of constant turbulence. The winds not only stir the atmosphere, but also transport material from the blistering hot day side to the freezing cold night side, resulting in a world of perpetual storm and chaos. In the upper reaches of the atmosphere, silicate particles condense into tiny droplets, which, driven by the planet's howling winds, fall back to the surface as molten glass rain. These molten droplets whip through the atmosphere with such force that they tear through the air with the intensity of an industrial storm. The very idea of such an environment is enough to send shivers down the spine, an alien world where storms are so extreme that they could melt metal and where the air itself seems hostile. Yet, this is the reality of HD 189733b, a planet where every element seems to be fine-tuned for survival in one of the most hostile and extreme climates in the galaxy. The vibrant, almost otherworldly colors of the planet, as seen through the lenses of telescopes, only add to the dreamlike strangeness of this far-off place, painting a picture of a world beyond our wildest imaginings. From its molten glass rains to its hurricane-force winds, HD 189733b is a striking reminder of how varied and bizarre planetary climates can be across the universe. It's a living, breathing example of the diversity of exoplanets, offering scientists and stargazers alike a glimpse into the unimaginable extremes that await in the farthest corners of our galaxy. In the grand scale of the universe, where conditions on Earth seem so unique and stable, HD 189733b reminds us that life, whether as we know it or not, can thrive in forms far beyond our comprehension. In July 2013, researchers utilizing the Hubble Space Telescope made a groundbreaking discovery. They successfully measured the color of HD 189733b, an exoplanet located in a distant star system. What they revealed was nothing short of astonishing: a deep azure blue, reminiscent of Earth's appearance from space. But unlike our home planet, where this blue hue is the result of sunlight scattering off atmospheric molecules and oceans, the reasons behind HD 189733b's striking color are far more extreme. The blue tint of this distant world originates not from oceans or skies, but from its turbulent atmosphere, a chaotic mix of silicate particles and possibly molten glass rain. These particles scatter blue light much more efficiently than red, lending the planet its unique and somewhat eerie appearance. This color measurement holds monumental significance. It marks one of the rare occasions when scientists have been able to observe and directly measure the visible color of an exoplanet, giving us a rare glimpse into the nature of a distant world. This type of data is invaluable, adding a tangible layer to our understanding of planets outside our solar system, that making them seem less abstract and more within reach. But the importance of this discovery goes far beyond just aesthetics. By analyzing the light that passes through the planet's thick atmosphere and reflects off its surface, scientists can infer critical details about the composition and conditions on this faraway world. The blue color, in particular, suggests the presence of a hazy, cloud-filled atmosphere, with particles large enough to scatter light in a way that gives the planet its striking blue appearance. This analysis enhances our understanding of gas giants with extreme weather patterns, contributing to our quest to catalog the vast array of planetary environments that exist across the universe. HD 18973b's proximity to its parent star makes it one of the most extreme exoplanetary environments ever observed. Situated just 4.7 million miles from its star, this planet is subjected to an unrelenting barrage of intense stellar radiation. To put this in perspective, Mercury, the closest planet to our Sun, is about 36 million miles away. The planet's close orbit results in tidal locking, where one hemisphere of the planet constantly faces its star, while the other remains locked in perpetual night. This configuration creates an extreme temperature gradient, with the day side reaching scorching temperatures of up to 1,000 degrees Celsius, while the night side remains far cooler. The intense heating on the planet's day side drives extraordinary atmospheric dynamics, including the formation of violent winds that can reach speeds of up to 5,400 miles per hour. These winds are not just a curious feature. They play a critical role in attempting to moderate the staggering temperature differences between the day and night sides of the planet. On top of that, the planet's proximity to its star means that its atmosphere is constantly bombarded by high-energy radiation. This radiation causes significant atmospheric evaporation, especially of lighter molecules like hydrogen, which leads to complex chemical reactions in the planet's upper atmosphere. Observations have shown that this relentless radiation may even strip away parts of HD 189733b's upper atmosphere, contributing to its volatile and ever-changing conditions. This constant bombardment from the star essentially transforms the planet into a chaotic laboratory, where scientists can study the effects of extreme radiation on planetary climates. These investigations are not just focused on understanding HD 18973b itself, but also on gaining insights into how exoplanets, especially those orbiting close to their stars, might evolve, and whether they might be habitable. In essence, the planet's unique and extreme nature offers a fascinating look at the broader forces that shape planetary atmospheres. Each discovery on HD 18973b helps to fill in the puzzle of how diverse and complex our universe truly is. As we continue to study this distant world, we inch ever closer to unlocking the mysteries of exoplanets and perhaps finding the building blocks for life beyond our own solar system. WASP-12b is a world that has captured the imagination of astronomers and exoplanet enthusiasts alike, earning its notorious reputation for being one of the hottest known exoplanets. Situated approximately 870 light-years away in the Orga constellation, this gas giant is about 1.8 times the size of Jupiter. However, it's not the sheer size or mass that makes WASP-12b so extraordinary. It's its extreme proximity to its parent star, WASP-12. This scorching relationship between the two results in conditions unlike any other planet we know. Orbiting its star at a distance of merely 2 million miles, just a fraction of the 28 million miles that separate Mercury from our Sun, WASP-12b is locked in an incredibly tight orbit. Its orbital period is incredibly short, completing one full revolution around its star in just over one Earth day. This means the planet is in a constant, unyielding sprint, exposed to relentless stellar radiation. As a result, the temperatures on WASP-12b's surface soar to a staggering 2,500 degrees Celsius, about 4,500 degrees Fahrenheit. This intense heat is not just a byproduct of its star's energy. It's the driving force behind the planet's most striking and alarming features. The extreme stellar radiation forces the planet's atmosphere to balloon out, expanding to nearly 3 times the radius of Jupiter. It's a bizarre sight, an inflated gas-filled bubble in space. However, this expansion isn't a stable condition. The tidal forces exerted by its star are slowly stripping away the planet's atmosphere, creating a trailing stream of gas that follows it through its orbit. This slow but relentless atmospheric erosion means that over time, WASP-12b is in the process of disintegration. If this continues unchecked, the planet could eventually be stripped entirely of its atmosphere, leaving behind only its core, a haunting thought for any planetary body. In a world where nothing seems stable, the chemical processes occurring on WASP-12b are equally fascinating and strange. The intense heat and radiation alter the planet's atmospheric composition, preventing reflective clouds from forming, and possibly even generating exotic materials like titanium oxide. These conditions lower the planet's albedo, causing it to absorb rather than reflect most of the incoming stellar radiation. The result is a catastrophic thermal state, further exacerbating its already searing temperatures. WASP-12b's unique and hostile environment is more than just a scientific curiosity. It offers vital insights into the behavior of planets that exist in extreme proximity to their parent stars, shedding light on the potential lifespan of such worlds and how their atmospheres evolve or even disintegrate. Furthermore, studying these extreme conditions helps broaden our understanding of the diversity of planetary environments across the galaxy, many of which are far from the hospitable conditions we experience on Earth. Another extraordinary characteristic of WASP-12b is the gravitational interaction between it and its parent star, which results in severe tidal forces. These forces stretch the planet into an elongated, egg-like shape, similar to the way Earth's moon affects our planet's tides. But these tidal forces aren't just a shape-shifting force, they also contribute significantly to the planet's already high temperatures. The friction generated by these tidal forces deep within the planet's interior causes significant tidal heating, further raising the temperatures to extreme levels. In summary, WASP-12b stands as a testament to the incredible diversity of exoplanets in our galaxy. Its extreme temperatures, rapid orbit, and gravitational interactions with its star make it a fascinating subject for scientific study. And while it may not be a place for life as we know it, it serves as a crucial reminder of the many bizarre and hostile environments that exist beyond our solar system. In addition to these tidal effects, WASP-12b is being gradually stripped of its atmosphere due to the intense radiation and gravitational tidal forces exerted by its star. This extraordinary phenomenon, known as atmospheric escape, results in a trailing stream of gas that is siphoned off into space, much like a comet's tail. Observations suggest that over time, this process could lead to the complete evaporation of the planet's atmosphere, potentially leaving behind nothing but a dense core, or perhaps stripping the planet entirely. WASP-12b's unique orbit, characterized by its extreme proximity to its star, provides an exceptional natural laboratory for studying the dynamic interactions between stars and their close-in exoplanets. This proximity offers scientists profound insights into the birth, evolution, and eventual fate of such extraordinary planetary systems. The planet was discovered as part of the Wide-Angle Search for Planets, WAT project, a ground-based survey designed specifically to find exoplanets using the transit method. This method involves monitoring the brightness of thousands of stars and looking for periodic dips in light, which occur when a planet passes in front of its star from our viewpoint on Earth. It was during such observations in 2008 that astronomers first detected the telltale signs of WASP-12b. The transit signal showed regular dips in the star's light, occurring every 1.09 days, indicating the presence of a large planet with an incredibly short orbital period. Follow-up observations using advanced spectroscopic techniques confirmed the planet's existence. These measurements, which analyzed the light spectrum of the star, allowed scientists to detect the gravitational influence of the orbiting planet and determine key properties of WASP-12b, such as its mass, size, and orbital characteristics. The discovery of WASP-12b was groundbreaking not only because of the extreme conditions found on the planet, but also for its role in refining the methods used to discover exoplanets. The combination of the transit method and follow-up spectroscopy validated the effectiveness of these techniques in identifying and characterizing distant worlds. Moreover, WASP-12b's discovery has since inspired a series of studies on close-in giant planets, providing valuable insights into the dynamics, composition, and evolution of these so-called hot Jupiters. This monumental find underscored the importance of collaborative astronomical surveys and the continual innovations in the field of exoplanetary science. WASP-12b's atmosphere is incredibly distinctive, marked by some of the most extreme and unusual conditions found on any known exoplanet. One of the planet's most notable features is its blistering temperature. Its close proximity to its parent star exposes it to relentless stellar radiation, heating its atmosphere to around 2,500 degrees Celsius or about 4,500 degrees Fahrenheit. This scorching heat places WASP-12b among the hottest known exoplanets, resulting in dramatic atmospheric phenomena. At such extreme temperatures, the atmosphere becomes a cauldron of exotic chemical reactions. One of the significant consequences of these intense conditions is the presence of molecules that would not typically be found in cooler environments. For instance, studies using the Hubble and Spitzer space telescopes have detected evidence of heavy elements like hydrogen cyanide, along with the potential presence of metals such as titanium oxide, both of which exist in gaseous form under the planet's extreme heat. These elements contribute to the atmosphere's exceptionally low albedo, making WASP-12b one of the darkest exoplanets ever observed. WASP-12b continues to challenge our understanding of exoplanets, providing a fascinating glimpse into the complex interactions between planets and their parent stars. Its extreme conditions make it a valuable subject of study, offering crucial insights into the fate of close-in planets, the formation of planetary systems, and the ultimate evolution of these remarkable worlds. As it absorbs at least 94% of the light that hits it rather than reflecting it, one of the most striking features of WASP-12b's atmosphere is its continuous loss into the vastness of space. This process, known as atmospheric escape, is driven by the intense radiation and powerful gravitational forces exerted by the planet's parent star. Gradually, the planet's atmosphere is being stripped away, creating a streaming tail of gas that drifts behind it, much like the trailing cometary tail. Observational data has revealed that the mass of WASP-12b's atmosphere is diminishing significantly over time, suggesting that one day it could be completely devoid of its gaseous envelope. This phenomenon offers an incredible window into the extreme environmental conditions of the planet, as well as providing valuable insights into the life cycle and evolution of exoplanets situated in similarly hostile orbits. WASP-12b stands as one of the most dramatic examples of the hot Jupiter class, a category of exoplanets known for their massive sizes and extreme proximity to their parent stars. Hot Jupiters share one key trait: their gas giant nature, with masses akin to Jupiter's, paired with blistering orbits that bring them dangerously close to their stars, subjecting them to sweltering heat. Yet, even in the context of hot Jupiters, WASP-12b takes planetary extremes to a new level. Orbiting at a mere 2 million miles from its star, it completes a full revolution in just over one Earth day. The immense tidal forces and intense stellar radiation it endures push it to unbearable temperatures, around 2,500 degrees Celsius, making it one of the hottest planets known. The gravitational pull from its parent star distorts the planet, giving it a stretched football-like shape. This is far from ordinary. While other hot Jupiters also face intense heating and tidal forces, the severity of WASP-12b's situation makes it one of the most extreme, fostering an environment unlike any other. Its rapid atmospheric loss, which is more pronounced than that of most hot Jupiters, further sets it apart. The outer layers of the atmosphere, superheated by radiation, expand and escape into space, trailing a gaseous stream behind the planet. This kind of atmospheric stripping is not commonly observed in other planets of the same class, making WASP-12b a crucial target for studying the long-term evolution of gas giants in close orbits. Additionally, the atmosphere of WASP-12b has shown chemical signatures such as hydrogen cyanide and possible titanium oxide, which point to high-temperature chemistry that differentiates it from many of its counterparts. While WASP-12b shares common traits with other hot Jupiters, such as high temperatures and significant radiation exposure, its extreme proximity to its star, along with the accompanying tidal and atmospheric effects, make it one of the most extraordinary examples of this already remarkable class of exoplanets. Its uniqueness not only challenges our understanding of planetary stability and longevity, but also enriches the broader study of planetary science, offering clues about the ultimate fate of close-orbiting gas giants. On the other hand, Kepler 452b, often referred to as Earth's cousin, offers an intriguing contrast. With several compelling similarities to our home planet, Kepler 452b stands as one of the most promising exoplanets in the search for potentially habitable worlds. Discovered by NASA's Kepler Space Telescope in 2015, this planet resides within the habitable zone of its parent star, Kepler 452. This Goldilocks zone is the region around a star where conditions are just right, not too hot, not too cold, for liquid water to exist on a planet's surface, the most critical ingredient for life as we know it. In this context, Kepler 452b ignites the imagination of scientists and dreamers alike, as it presents a fascinating possibility. Could this distant world be the next home for life beyond Earth? By examining the features of planets like WASP-12b and Kepler 452b, scientists can better understand the vast diversity of exoplanets that populate our galaxy and what their extreme conditions can teach us about the potential for life in the universe. Kepler 452b has captivated the interest of astronomers and space enthusiasts alike due to its striking similarities to Earth. One of the most compelling aspects of Kepler 452b is its size and estimated mass. This exoplanet is roughly 1.6 times the diameter of Earth, a size that places it in the category of super-Earths, planets that are larger than Earth but not as massive as the gas giants like Uranus and Neptune. While the precise mass of Kepler 452b remains uncertain, it's believed to be about 5 times more massive than our planet. These dimensions suggest that Kepler 452b could have a stable atmosphere, possibly capable of supporting weather patterns, and maybe even life, similar to what we experience here on Earth. What truly sets Kepler 452b apart, however, is its parent star, Kepler 452. This star shares remarkable similarities with our own sun, even though it is about 1.5 billion years older. This age difference is significant, as it suggests that Kepler 452b has had the potential to host life for a longer period, just as life has had time to evolve on Earth. The fact that Kepler 452b orbits within its star's habitable zone and receives a comparable amount of solar energy to what Earth receives from the sun makes it an even more intriguing candidate for supporting life. In fact, Kepler 452b stands out as one of the most Earth-like exoplanets discovered to date. It not only shares a similar size and orbital position, but also resides in the habitable zone of a sun-like star. This zone is where liquid water could potentially exist, one of the key requirements for life as we know it. The question remains, could life actually thrive there? While many exoplanets have been discovered, Kepler 452b's similarity to Earth, particularly its size, location, and proximity to a stable, sun-like star, offers a rare and valuable glimpse into what other Earth-like worlds might exist in the universe. This discovery adds layers to our understanding of the cosmos and encourages us to imagine a broader place for humanity in the vastness of space. Kepler 452 orbits its star, Kepler 452, in ways that mirror the relationship between the Sun and Earth. Kepler 452 is classified as a G-type main sequence star, like our Sun. This means that the two stars share a similar spectral type, crucial for determining the potential habitability of their planets. Despite their similarities, Kepler 452 is older, about 1.5 billion years more advanced in its stellar life cycle. This age difference is key to understanding the potential effects on Kepler 452b. The older age of Kepler 452 implies that it has already begun to expand and brighten due to the accumulation of helium in its core, which changes its energy output and the habitable zone around it. As stars age, they become brighter and larger, which affects the planets in their orbit. Kepler 452 is about 10% larger in diameter and 20% more luminous than our Sun, meaning that Kepler 452b receives 10% more energy than Earth. This additional energy could alter the planet's climate and atmospheric conditions. The increased luminosity might lead to higher surface temperatures, which could influence the planet's ability to support life or cause its atmosphere to behave in unexpected ways. However, the star's long and stable nature offers a unique opportunity for life to evolve, provided other factors, such as the planet's composition and atmospheric conditions, are conducive to life. The comparison between Kepler 452 and the Sun offers not only an exciting glimpse into the possibilities of extraterrestrial life, but also helps scientists understand the variety of evolutionary paths that stars and their planets can follow. Kepler 452's advanced age paired with its increased luminosity presents a fascinating case study for understanding how stars and planets evolve over time. The fact that the star is still stable and long-lived provides an extended time frame in which any biological processes could potentially develop, adding depth to our understanding of the potential for life elsewhere in the galaxy. Kepler 452b, with its orbit size and location in the habitable zone of its parent star, remains one of the most Earth-like exoplanets discovered so far. Its comparison to Earth in terms of size, its place within the habitable zone of a Sun-like star, and the potential for liquid water offer an incredible opportunity to explore how life might thrive beyond our world. The discovery of Kepler 452b enriches our understanding of the universe and our place in it, reminding us that we are not alone in the vast cosmos. Situated approximately 1,400 light-years away in the constellation Cygnus, Kepler 452b orbits its G-type star, Kepler 452, in a zone often referred to as the habitable zone. This critical region, also called the Goldilocks zone, is the sweet spot around a star where conditions might be just right for liquid water to exist on a planet's surface, an essential ingredient for life as we understand it. Kepler 452b's unique position within this zone is what first captured the scientific community's attention, offering tantalizing possibilities for habitability. One of the most intriguing aspects of Kepler 452b is its orbital period. The planet completes one full orbit around its star in about 385 Earth days, giving it a year only slightly longer than our own. This relatively similar orbital period means that Kepler 452b receives sunlight in quantities comparable to Earth, enhancing its potential to host life. Its orbital distance from Kepler 452 is about 1.05 astronomical units, nearly identical to the distance between Earth and our Sun. This similarity is crucial, as it suggests that Kepler 452b could enjoy a thermal environment close to Earth's, further strengthening its case as a prime candidate for the presence of liquid water. Despite its many Earth-like qualities, Kepler 452b is not identical to our home planet. It is approximately 6 times the diameter of Earth, placing it in the category of super-Earths. Its mass is estimated to be about 5 times that of Earth, although precise measurements remain elusive without direct gravitational data. These characteristics suggest that Kepler 452b is likely a rocky planet, much like Earth, but with a higher gravitational pull. This increased gravity might play a significant role in maintaining a thick atmosphere, which could regulate surface temperatures and create conditions conducive to life. Kepler 452b's size, orbit, and proximity to its star present compelling parallels to Earth. Its location within the habitable zone and its larger size hint at a potentially rocky composition, positioning it as one of the most promising candidates in the search for extraterrestrial life. These factors fuel ongoing interest in this distant world, which remains a focal point of scientific inquiry. Discovered through NASA's Kepler Space Telescope, launched in 2009, Kepler 452b's identification was made possible by the transit method. This technique involves monitoring the brightness of stars for periodic dips in light, which occur when a planet passes in front of its host star. For Kepler 452b, these dips were observed in the star Kepler 452's light curve, leading astronomers to deduce that the planet's orbital period was around 385 days, just like Earth's year. The transit method not only confirmed the planet's presence, but also provided essential data on its size and distance from its star. Once identified, Kepler 452b's discovery was cross-checked with additional data to rule out false positives caused by factors such as stellar activity or binary star systems. The confirmation of the planet's existence came in 2015 during an official NASA press conference. This milestone further underscored the success of the Kepler mission, which sought to identify Earth-like exoplanets in habitable zones across the galaxy. The discovery of Kepler 452b was seen as one of the most significant in the quest to find planets capable of supporting life beyond our solar system. What makes Kepler 452b even more fascinating is its host star, which shares remarkable similarities with our own Sun. Although Kepler 452 is about 10% larger and brighter than our Sun, it shares many of the same stellar characteristics. What makes it particularly significant is its age. At 1.5 billion years older than the Sun, Kepler 452 offers a glimpse into the future of our own star, providing scientists with valuable insights into how older stars impact the potential habitability of their planets. Kepler 452b's size is another crucial feature. About 60% larger in diameter than Earth, it falls into the category of super-Earths, which are planets that are more massive than Earth, but still rocky. This suggests that Kepler 452b could possess a solid surface and a thick atmosphere, although further investigations are necessary to confirm these assumptions. The discovery has sparked considerable interest in how older stars like Kepler 452 may affect the longevity of habitability on planets, offering potential insights into Earth's own future in billions of years. This discovery highlights not only the incredible capabilities of the Kepler Space Telescope, but also the importance of the transit method in the study of exoplanets. Kepler 452b is an exceptional candidate for further exploration as it remains one of the most promising analogs to Earth found so far in the vast cosmos. As research continues, Kepler 452b's potential for habitability makes it an exciting focal point in the ongoing search for life beyond our planet. Kepler 452b has captivated both the scientific community and the general public alike, offering hope in the search for extraterrestrial life. As scientists continue to study this distant world, the possibilities it presents are boundless, reinforcing the idea that Earth may not be alone in the universe. In the vast expanse of space where the wonders of the cosmos unfold before our eyes, one distant world stands out with a name that echoes through history and myth. HD 29458b, often called Osiris, is not just an exoplanet, it is a cosmic enigma, a world that bridges the ancient and the astronomical, merging the realms of myth and science. Named after the Egyptian god Osiris, who represents the cycles of death, resurrection, and the fertility of the Nile, this exoplanet holds a striking parallel to its namesake's mythological journey. Just as Osiris faced dismemberment and rebirth, HD 29458b undergoes a relentless transformation, forever changing under the powerful forces acting upon it. Osiris, in Egyptian myth, was torn apart by his brother Set, only to be resurrected by his wife Isis, symbolizing the eternal cycle of death and rebirth. In much the same way, HD 29458b faces its own cycles of transformation. A hot Jupiter, a type of gas giant that orbits dangerously close to its star, this exoplanet experiences extreme conditions, such as blistering temperatures and intense stellar radiation. These forces are so profound that the planet's atmosphere begins to evaporate, its outer layers stripped away in a process called atmospheric escape. This dramatic phenomenon mirrors Osiris's mythical death and resurrection, reminding us of the relentless forces at play in the universe. The name Osiris not only captures the planet's mythological resonance, but also serves a practical purpose. By invoking a name already rich with meaning, the scientific community and the public alike can more easily internalize the complex nature of HD 29458b. The atmospheric features of this world, including a striking comet-like tail caused by the intense heat it endures, evoke powerful imagery. The name serves as a cultural bridge, making the distant, abstract nature of exoplanets more relatable and engaging. This helps both scientists and lay people to conceptualize the planet, transforming it from an impersonal celestial body into a world with a story, one that stretches from ancient Egyptian myth to cutting-edge astronomical discovery. But HD 209458b is much more than just a name. It is a key to understanding the dynamics of planetary atmospheres and the evolution of distant worlds. As the first exoplanet where an atmosphere was directly detected, it has paved the way for an entire field of study dedicated to uncovering the complexities of these far-off planets. Through detailed observation of the planet's atmosphere, scientists have been able to identify a range of chemical elements and compounds, including sodium, hydrogen, carbon, and oxygen. This rich chemical profile not only gives us a glimpse into the planet's formation, but also allows researchers to explore the physical and chemical processes that shape its atmosphere, providing vital clues about its age and history. Moreover, HD 294558b has given us the first direct evidence of atmospheric escape, a crucial phenomenon for understanding planetary evolution. As stellar radiation and powerful winds strip away the planet's outer layers, we are reminded of the fragile nature of planetary atmospheres. This process has profound implications for our understanding of planetary habitability, as the loss of an atmosphere can drastically alter a planet's potential to support life. By studying HD 29458b, scientists gain valuable insights into how planetary atmospheres evolve and how this affects the long-term stability and habitability of distant worlds. The study of water vapor in HD 29458b's atmosphere further complicates and enriches our understanding of exoplanetary climates. The delicate balance between atmospheric chemistry and temperature dynamics plays a vital role in the potential for life to exist on a planet. As scientists continue to unravel the mysteries of this unique world, their findings contribute to a deeper understanding of the factors that govern planetary systems and the environments that could support life, whether on Earth or on distant exoplanets. The study of HD 29458b extends beyond scientific inquiry. It is an exploration of the human spirit's quest to understand the unknown. As we probe the secrets of this far-off world, we are also deepening our understanding of our own planet's history and future. From the origins of our atmosphere to the delicate balance required to sustain life, the knowledge gained from HD 2094588b informs our models of Earth's own evolution, providing a mirror through which we can better understand our place in the universe. This mythologically inspired naming tradition, the exploration of planetary atmospheres, and the pursuit of knowledge serve as a testament to our unyielding curiosity and our relentless drive to explore the mysteries of the cosmos. HD 2094588b is a standout exoplanet, playing a pivotal role in the advancement of exoplanetary science and atmospheric studies. This hot Jupiter, situated just 7 million kilometers away from its parent star, endures intense stellar radiation. Such proximity subjects it to extreme atmospheric conditions, offering scientists a natural laboratory for understanding planetary atmospheres in alien environments. The planet's proximity, combined with its substantial size, around 0.69 times the mass of Jupiter but with a larger radius, creates powerful atmospheric signals that are ideal for study. But what truly sets HD 29458b apart is its ability to transit across its parent star from our vantage point on Earth. These transit events, where the planet moves in front of the star, provide a unique opportunity for scientists to study the atmosphere in unprecedented detail. The transmission of starlight through the planet's atmosphere reveals crucial information about its chemical composition, dynamics, and even its temperature profiles. This is made possible through the technique of transmission spectroscopy, which enables the detection of key elements and molecules in the planet's atmosphere, such as sodium, carbon, oxygen, and even water vapor. The wealth of data collected through these observations is invaluable for refining and calibrating atmospheric models, ensuring more accurate future studies of exoplanet atmospheres. HD 2094588b holds a monumental place in the history of exoplanetary science, as it was the first exoplanet where an atmosphere was directly detected. This groundbreaking discovery was made during a transit event where the starlight filtering through the atmosphere offered the first direct evidence of its gaseous composition. This was achieved using the Hubble Space Telescope, which has since played a key role in identifying various elements within the atmosphere of HD 209458b. The planet's atmosphere behaves predictably, confirming that elemental and molecular interactions observed here on Earth are consistent even in distant, extrasolar environments. This validation is crucial for building a more refined understanding of atmospheric science. The data obtained from HD 209458b also serves to underscore the reliability of transmission spectroscopy as a method for studying distant exoplanets. It has become an indispensable tool for further investigations of planetary atmospheres, enhancing the precision with which scientists can model exoplanetary environments. The impact of this discovery extends far beyond just one planet. It has opened doors for future research into the atmospheres of other exoplanets, advancing our understanding of what makes Earth-like conditions possible on distant worlds. HD 29458b's place in exoplanet history was further cemented by its role as one of the first exoplanets discovered using the transit method. This technique involves monitoring periodic dips in a star's brightness as a planet transits across it, blocking a fraction of the light. This method revolutionized the way we detect and study exoplanets, as it provides direct evidence of a planet's existence and allows for precise measurements of its size and orbital characteristics. The discovery of HD 209458b was first announced in 1999, a momentous occasion in the burgeoning field of exoplanetary science. The initial detection of HD 29458b was actually made through radial velocity measurements, a technique that observes slight shifts in a star's position caused by the gravitational influence of an orbiting planet. Ground-based telescopes first identified these wobbles, suggesting the presence of a large planet orbiting close to its star. However, the real breakthrough came when astronomers observed the planet transiting across its star, providing irrefutable proof of its existence. This discovery was not only the confirmation of the planet's presence, but also allowed for detailed studies of its size, mass, and orbital parameters, all with a high degree of precision. Following this, HD 29458b became a target for detailed atmospheric studies, as its transits allowed astronomers to analyze the starlight passing through its atmosphere. This enabled them to break down the chemical makeup of the atmosphere in ways that had never been possible before. The combination of radial velocity and transit observations made HD 29458b a pioneering target for exoplanet research, setting the stage for future discoveries about distant worlds. It remains a vital object of study, shaping our understanding of exoplanetary systems and the environments of planets orbiting distant stars. As scientists continue to explore the mysteries of planets like HD 209458b, they build on the foundational discoveries it helped make possible, advancing the field of exoplanet research. This hot Jupiter has provided us with unparalleled insights into the composition of alien atmospheres, offering clues that may one day help us find habitable worlds beyond our solar system. Discovered in 2009, the exoplanet GJ-124b orbits a red dwarf star located approximately 42 light-years from Earth in the constellation Ophiuchus. This planet stands out with a radius about 2.7 times that of Earth and a mass roughly 6.5 times greater, positioning it firmly within the super-Earth category. This classification is crucial because it suggests that GJ-124b might have a composition more akin to Earth or Neptune, rather than the larger gas giants, providing unique insights into the diversity of planetary systems that may exist throughout the galaxy. What truly makes GJ-124b captivating is its atmosphere, which has been the subject of intense scrutiny since its discovery. Unlike many other exoplanets, GJ-124b has a thick, cloudy atmosphere, which some scientists believe could be rich in water vapor or even hydrogen. Spectroscopic observations hint at the possibility of a substantial water presence, either in the form of vapor or as part of a deep, possibly global ocean. This has led to the intriguing notion that GJ-124b could be a water world, a type of exoplanet with an atmosphere and surface that bear significant resemblance to Earth's water-rich environment. This atmospheric composition challenges existing models of planetary formation and provides valuable clues about the conditions required for habitability. Due to its proximity to Earth, GJ124b is an excellent candidate for detailed atmospheric studies using both current and next-generation telescopes. These studies could help to unravel the complexities of super-Earth atmospheres, advancing our understanding of the types of planets that might be more common in the galaxy than we once thought, and potentially paving the way for future discoveries related to extraterrestrial habitability. The discovery of GJ124b was made using the transit method, a technique that has become one of the most effective tools for discovering and studying exoplanets. This method involves observing the dimming of a star's light as a planet passes in front of it from our line of sight. GJ124b was discovered by the MIRI Mega Constellation Infrared Project, an initiative that employs an array of ground-based robotic telescopes specifically designed to monitor nearby small stars for transiting planets. The project focuses on M-dwarf stars, which are smaller and cooler than our Sun, making it easier to detect smaller, Earth-sized planets due to the more pronounced dimming effect that occurs when a planet transits its star. In December 2009, astronomers observed a periodic dimming in the light of the red dwarf star GJ124b, located 42 light-years away in the constellation Ophiuchus. This dimming indicated that an object was periodically passing in front of the star. Subsequent observations confirmed that the dimming was caused by a planet-sized object transiting the star. Further analysis of the transit data allowed scientists to calculate the size and orbital period of the planet, revealing that GJ124b completes an orbit around its star in just under 38 hours. After the initial discovery, additional observations were made using both ground-based and space telescopes, allowing scientists to refine the planet's mass and density. This confirmed that GJ124b is indeed a super-Earth, with a radius approximately 2.7 times that of Earth and a mass about 6.5 times greater. The planet's thick atmosphere, potentially rich in water vapor or hydrogen, sparked significant interest, prompting extensive follow-up studies. This discovery not only expanded the catalog of known exoplanets, but also highlighted the potential for finding Earth-like planets around M-dwarf stars, which are abundant in our galaxy. The findings surrounding GJ124b are just the beginning of a much larger quest to understand the variety of exoplanets that populate our universe. As astronomers continue to study GJ124b, it could provide crucial clues about the conditions necessary for life beyond Earth, especially among the vast number of planets orbiting cooler, smaller stars. With the help of advanced telescopes, the mysteries of this unique planet will continue to unfold, offering a glimpse into the diverse worlds that may exist in the far reaches of space. The atmosphere of GJ124b is one of the most captivating and mysterious aspects of this exoplanet, drawing the attention of scientists ever since its discovery. From the moment it was observed, its thick, cloud-covered atmosphere stood out as an enigma, one that has sparked extensive research and debate. This dense and hazy layer, which shrouds the planet's surface, presents a significant challenge for astronomers trying to unravel the planet's true composition. Early observations by the Hubble Space Telescope suggested that the planet's atmosphere could be rich in water vapor or hydrogen, leading to the intriguing hypothesis that GJ124b might be a water world, a planet where water could dominate, enveloped by a dense, steamy atmosphere unlike anything we had seen before. As scientists dove deeper into studying GJ124b, they found that the planet's atmosphere didn't follow the patterns that would be expected for a clear, transparent layer. Spectroscopic data revealed the absence of strong atmospheric features, which would normally indicate a clearer composition. Instead, the planet's atmosphere was obscured by thick clouds or haze, making it incredibly difficult to look deeper beneath the surface. While the exact composition of these clouds remains uncertain, there are speculations that they might be composed of water droplets, hydrocarbon compounds, or possibly even more exotic materials. The thick atmosphere of GJ124b creates a significant barrier to understanding what lies beneath. However, data suggests that the planet likely has a high molecular weight in its atmosphere, which could point toward a rich, water-heavy composition. The challenge of determining the planet's internal structure only adds to the allure of this enigmatic world. But the implications of GJ-124b go far beyond just one exoplanet. It serves as a living laboratory, a natural testing ground for scientists to better understand how planets transition from rocky terrestrial bodies to gas giants. The discovery of water vapor, or hydrogen, in GJ-124b's atmosphere supports several models that predict a range of planetary outcomes, depending on factors like their distance from their host stars and their evolutionary paths. This makes GJ-124b an invaluable tool for understanding not only the planet itself, but also the broader categorization of exoplanets. It helps refine our methods and techniques for studying other similar planets, but especially those in the super-Earth category. These super-Earths, which are thought to be prevalent in our galaxy, are planets with masses and sizes larger than Earth's, but smaller than gas giants. Understanding their atmospheres is crucial for future studies. GJ-124b holds a prominent place in the study of super-Earths. With a radius about 2.7 times that of Earth and a mass roughly 6.5 times greater, it resides in a unique range of planet sizes that challenge traditional planetary formation models. Its position, approximately 42 light-years away, makes it an ideal target for both current and future generations of telescopes. This relative proximity allows astronomers to conduct detailed and repeated observations, which are critical for understanding the complex properties of its atmosphere and composition. The planet's thick, opaque atmosphere is one of the main reasons for the significant attention GJ-124b receives in the scientific community. This haze serves as both a puzzle and a laboratory, enabling scientists to test and refine their tools for studying exoplanets. One of the most exciting possibilities is that GJ-124b could be a true water world, with water vapor and hydrogen in abundance. This would open up new avenues for understanding the diversity of planetary compositions within the super-Earth category. Super-Earths are thought to be among the most common type of exoplanets in our galaxy, yet their range of possible compositions and structures remains largely unexplored, making them a critical focus for planetary science. As our tools and understanding continue to evolve, the study of GJ-124b will undoubtedly play a pivotal role in shaping the future of exoplanet research. It offers a glimpse into the vast diversity of worlds that exist beyond our solar system, pushing the boundaries of what we know and challenging us to think beyond the confines of our own planet. In the vastness of space, GJ-124b offers an intriguing glimpse into the complexities of planetary environments. Orbiting a relatively small and dim red dwarf star, this exoplanet presents a unique opportunity for scientists to study the effects of stellar radiation on atmospheric properties. These interactions provide vital insights into the habitability potential of super-Earths orbiting various types of stars, shedding light on how planets form, evolve, and which conditions might support life. GJ-124b isn't just another planet in the distant cosmos. It holds the key to unlocking the mysteries of planetary diversity and the many paths super-Earths can take in developing and sustaining different atmospheres. GJ-124b's allure stems from its unique combination of size, mass, and thick atmosphere, characteristics that pose both fascinating possibilities and significant challenges for the notion of habitability. The planet has a radius approximately 2.7 times that of Earth and a mass around 5 times greater, making it difficult to classify into the traditional categories of terrestrial or gas giant planets. This size gives it a substantial gravitational pull, likely affecting any surface conditions, creating an environment that doesn't easily compare with Earth's. While this raises interesting questions about its potential for supporting life, it also presents challenges that current data suggest could make life, as we know it, highly unlikely. The most promising aspect of GJ-124b lies in its thick, possibly water-rich atmosphere. There's a tantalizing hypothesis that the planet could be a water world, with significant amounts of water vapor or even oceans hidden beneath a cloudy, dense atmosphere. This notion fuels speculation that, in some form, environments suitable for life could exist. However, the reality, based on current scientific evidence, paints a more complex picture. The atmosphere is believed to be dense and steamy, leading to surface pressures and temperatures much higher than those on Earth. These extreme conditions present formidable barriers for life as we know it, making the prospect of habitability less likely in the conventional sense. Adding another layer of complexity, GJ1240b orbits a red dwarf star, a type of star that, while providing a stable light source, is known for its variability and the potential for significant stellar flares. These flares could strip away atmospheric layers or subject the planet to harmful bursts of radiation. Although GJ1240b's thick atmosphere might offer some shielding, it also suggests that the planet's surface, if it exists in a conventional sense, would likely be inhospitably hot and under immense pressure. This paints a picture of an environment that is far from Earth-like, perhaps more akin to the extreme conditions found in the deep ocean vents on our own planet, but on a much larger and more intense scale. While GJ1244b remains an accessible object for study and offers valuable insights into the range of planetary environments, its prospects for habitability are currently considered low. The extreme conditions predicted by its atmospheric and physical properties create an environment that differs greatly from Earth, possibly making it impossible for life as we understand it to survive or thrive. However, future missions and advanced observational techniques may offer more definitive answers, helping to clarify the boundary conditions for habitability, not just on GJ1240b, but also for other super-Earths scattered across our galaxy. The study of this distant planet continues to illuminate the wide array of possibilities for how planets can evolve and whether life might exist elsewhere in the universe. LHS 1140b has captivated the attention of the scientific community, emerging as one of the most intriguing candidates for habitability in the search for life beyond Earth. Discovered in 2017, this exoplanet orbits a red dwarf star named LHS 1140, which is located just 41 light years away from our planet, astonishingly close in cosmic terms. This proximity alone makes LHS 1140b an object of intense scientific interest. However, it is the planet's unique characteristics that truly set it apart as a potential haven for life. Positioned within the star's habitable zone, LHS 1140b lies in the region where conditions might support the existence of liquid water on its surface. Liquid water is considered a crucial ingredient for life as we understand it, acting as a vital solvent in biochemical processes. This fact alone places LHS 1140b at the forefront of exoplanetary research. But what makes this planet even more fascinating is its size and density. LHS 1140b's radius is roughly 1.4 times that of Earth, and its mass is nearly 7 times greater. These physical characteristics imply a rocky composition similar to our own planet. The higher density suggests a solid surface, an essential factor when considering habitability, as it indicates the possibility of a stable, Earth-like environment. One of the most promising aspects of LHS 1140b's composition is its gravity. The planet's larger mass and higher density likely result in stronger gravity, which could play a crucial role in maintaining a stable atmosphere over geological timescales. This is vital because it reduces the likelihood of atmospheric escape, a process in which a planet loses its atmosphere to space, thereby rendering it inhospitable. A stable atmosphere is also key to maintaining temperate surface conditions that could support life. Moreover, LHS 1140b's slow orbital period of about 25 days means it could enjoy more moderate climate conditions, further increasing the chances of habitable surface temperatures. But there is another factor that makes LHS 1140b particularly enticing: its host star, LHS 1140 itself. Unlike many other red dwarfs, LHS 1140 is relatively calm and exhibits minimal stellar variability. Red dwarf stars are known for their intense and frequent flares, which can emit harmful radiation capable of stripping away a planet's atmosphere. This poses a major challenge for life development. However, LHS 1140's relatively quiet nature minimizes these risks, providing a more stable environment for the planet and reducing the chances of disruptive radiation. As a result, LHS 1140b might stand a better chance of retaining a life-supporting atmosphere than other planets orbiting more active red dwarfs. The potential for LHS 1140b to support life hinges not only on its location within the habitable zone, but also on the unique characteristics of its host star. Red dwarfs, while smaller and cooler than stars like our Sun, can burn for billions of years, maintaining relatively stable luminosity over time. This long lifespan could ensure a more consistent environment on LHS 1140b, allowing life-supporting conditions to persist for much longer periods compared to planets orbiting more volatile stars. This stability could increase the chances of life emerging and thriving on the planet if conditions are right. LHS 1140b's favorable location in the habitable zone, its rocky composition, and its host star's calm nature make it an exciting candidate for further investigation. Scientists are eager to study the planet's atmosphere using advanced telescopes, hoping to detect signs of water, oxygen, or other biomarkers that could indicate the presence of life. LHS 1140b stands as one of the most exciting prospects in the search for habitable exoplanets, bridging the gap between planetary science and the tantalizing quest to answer the age-old question, are we alone in the universe? With every new discovery about this distant world, we edge closer to understanding whether life can exist beyond Earth, making LHS 1140b one of the most important targets for exoplanetary research in the years to come. Imagine the possibility of life thriving on a planet orbiting a distant star. This scenario comes to life when we look at the infrared wavelengths emitted by red dwarf stars like LHS 1140. These wavelengths, unlike ultraviolet or visible light, can penetrate planetary atmospheres more effectively, distributing energy in a way that creates a warming effect. This not only helps maintain liquid water on the planet's surface, but also fosters a potentially habitable environment. LHS 1140, the host star of the exoplanet LHS 1140b, is a relatively quiet, long-lived red dwarf. Its stable energy output and the planet's slow orbital period of approximately 25 Earth days work together to create an environment that balances temperature over the course of the planet's year. This makes LHS 1140b a unique candidate for supporting life. The star's benign influence, combined with the planet's ideal positioning in the habitable zone where liquid water could exist, lays the foundation for the possibility of life. LHS 1140b's orbit, at a mere 25-day period, places it close to its host star, but still within the habitable zone. This positioning is vital. It offers the potential for temperate climates, a crucial factor for sustaining life. And despite its proximity to its star, the planet benefits from the lower intensity of radiation emitted by the red dwarf. This results in moderate temperatures that help preserve a stable environment, far from the extremes that could strip away an atmosphere or prevent the development of life. With a radius about 1.4 times that of Earth and a mass nearly 6.6 times greater, LHS 1140b is classified as a super-Earth, larger than our own planet but smaller than the ice giants like Uranus and Neptune. This makes it a particularly intriguing object of study. Its higher density suggests a rocky composition similar to Earth, and its significant mass allows it to retain a thick atmosphere. Such an atmosphere enhances the potential for stable conditions on the surface, which is critical for habitability. Additionally, the planet's synchronous rotation, a common feature in close-orbiting exoplanets, means that one hemisphere is always facing its star, while the other remains in eternal darkness. Despite this, the twilight zone, or the terminator region between the two hemispheres, could still offer habitable conditions, as it allows for a more balanced distribution of light and temperature. These unique characteristics of LHS 1140b make it more than just another super-Earth. With its ideal positioning, stable environment, and potential for liquid water, it stands out as one of the most compelling candidates for future exploration. The combination of the planet's size, orbit, and the star's gentle radiation output creates a promising scenario for discovering whether life, in some form, could exist beyond our own Earth. The search for habitable exoplanets is one of the most exciting scientific endeavors today. LHS 1140b, with its fascinating features, not only offers insight into the possibilities of life beyond our solar system, but also offers hope for future generations to explore the stars in search of answers. Located within the habitable zone of its star, LHS 1140b presents a unique opportunity to explore the possibility of life beyond our own solar system. The planet's significant rocky mass, combined with its optimal position in the habitable zone, sets the stage for an array of scientific investigations aimed at understanding its potential for harboring life. The discovery of LHS 1140b, a rocky exoplanet, was made possible through the use of the transit method, a technique that has revolutionized our ability to detect and study exoplanets. This method involves observing small dips in the brightness of a star as a planet passes in front of it, a process known as a transit. When these periodic dips are detected, they provide crucial data about the planet, including its size, orbital period, and other key characteristics. In the case of LHS 1140b, these transits were observed and studied meticulously, revealing the planet's fascinating properties. The discovery, announced in 2017, was the result of a collaborative effort led by an international team of astronomers from the Harvard-Smithsonian Center for Astrophysics. The team worked alongside the MERTH project, which utilizes an impressive network of ground-based robotic telescopes located in Arizona and Chile. The MERTH project is specifically designed to monitor nearby red dwarf stars, making it particularly adept at identifying Earth-sized and super-Earth planets around these relatively faint stars. The project has played a critical role in our ability to detect exoplanets around red dwarfs, which are among the most common types of stars in the universe. During the observation campaign, astronomers noticed that the star LHS 1140 exhibited consistent dimming events at regular intervals, suggesting the presence of a planet passing in front of it. Through detailed analysis, they confirmed that these dips in brightness were indeed caused by a planet, and further investigations revealed that this planet, LHS 1140b, transited its star every 25 days. To confirm these findings, the team used the HARPS spectrograph at the European Southern Observatory's La Silla Observatory in Chile, allowing them to measure the planet's radial velocity and calculate its mass. The combined data from the transit method and radial velocity measurements revealed that LHS 1140b has a radius approximately 1.4 times that of Earth and a mass about 6.6 times greater, making it a rocky super-Earth. This discovery highlights the incredible precision and collaborative power of modern exoplanet discovery methods. It underscores how sophisticated our techniques have become, allowing us to detect planets even around relatively faint red dwarf stars. LHS 1140b's discovery not only expanded the list of intriguing exoplanets, but also provided a prime candidate for further investigation into the conditions necessary for life beyond our solar system. Its rocky composition and position within the habitable zone make it an ideal subject for studies exploring planetary formation and habitability. Situated about 40 light-years away in the constellation Cetus, this planet is particularly compelling because of the possibility that liquid water could exist on its surface. This makes LHS 1140b a key target for future research, potentially revealing insights into the broader question of whether life could thrive beyond Earth. The planet's mass, density, and composition suggest that it is predominantly made of rock, with the potential to harbor an atmosphere, another crucial factor for supporting life. As such, LHS 1140b offers an invaluable opportunity for scientists to delve deeper into the study of exoplanetary atmospheres, the conditions required for life, and the broader implications of discovering habitable worlds beyond our own. This captivating exoplanet remains a cornerstone of ongoing research in the search for life beyond the solar system, providing hope that one day we might uncover the secrets of life on planets far beyond Earth. LHS 1140b presents one of the most captivating mysteries in the cosmos, and its allure is further intensified by its remarkable age and stability. Orbiting the mature red dwarf star LHS 1140, this exoplanet exists in a system that has withstood the test of time. LHS 1140, aged in the billions of years, offers a rare glimpse into the long-term dynamics of stellar evolution. The longevity of the star suggests that the environment surrounding its planets, including LHS 1140b, has had ample time to evolve, potentially developing conditions capable of supporting life. In particular, LHS 1140's relatively low levels of stellar radiation, especially when compared to younger red dwarfs, which often emit intense flares, allow for the possibility that the planet's atmosphere has remained stable over time. This stability makes LHS 1140b an outstanding candidate for future missions designed to probe for biosignatures. Researchers are keen to examine whether complex chemical processes, which could be indicative of life, have taken root on this planet. Additionally, LHS 1140b is a key focus for theorists aiming to better understand the environments of rocky exoplanets in the broader universe. Its status as a stable, long-lived world offers insights into how other planetary systems might evolve and develop. In stark contrast, 55 Cancri e, a rocky exoplanet located approximately 40 light-years away in the constellation Cancer, presents an environment so extreme it defies conventional understanding. Orbiting its host star, 55 Cancri a, at an astonishingly close distance of just 0.015 astronomical units, roughly 25 times closer than Mercury is to our Sun, this planet endures some of the most extreme surface conditions ever discovered. With a blistering orbital period of only 18 hours, 55 Cancri e is bombarded by intense stellar radiation, pushing daytime temperatures to over 2,000 degrees Celsius, hot enough to melt and vaporize rock. This intense heat, coupled with the planet's formidable gravity, roughly 8 times that of Earth, creates an environment of extreme pressure and searing surface conditions. Scientists speculate that 55 Cancri a may possess vast oceans of molten lava, perhaps mixed with volatile substances like carbon and nitrogen gases. These intense conditions are further complicated by a puzzling discrepancy in heat distribution, where the day side of the planet is vastly hotter than the night side. This could be due to a number of factors such as complex atmospheric dynamics or a form of partial molten lava flow. Regardless of the precise cause, the result is a landscape unlike any other in our solar system, fueling scientific speculation about its unique geological structure and potential for volatile rich compositions. The discovery of 55 Cancri a was made possible through the combined efforts of 2 primary detection techniques: the radial velocity method and the transit method. In 2004, astronomers first detected the presence of a super-Earth-sized planet orbiting the star 55 Cancri a using the radial velocity technique, which measures the wobble of a star caused by gravitational interactions with orbiting planets. This initial detection marked the beginning of the journey to understand the planet's extraordinary characteristics. In 2011, the transit method was used to confirm the planet's existence. By observing the slight dimming of the star's light as 55 Cancri a transited in front of it, scientists were able to gather more detailed data, including the planet's size and composition. NASA's Spitzer Space Telescope played a crucial role in this phase, providing vital information that confirmed the planet's extreme surface conditions and its incredibly short orbital period. 55 Cancri e, with its blistering temperatures, high gravity, and rapid orbit, serves as a natural laboratory for studying the limits of planetary environments. As one of the first super-Earths to reveal such extreme properties, it offers invaluable insights into how rocky planets can endure intense stellar conditions, opening the door to future investigations into the resilience of exoplanets in far-flung corners of the universe. Discovered orbiting its star 55 Cancri a, 55 Cancri e reveals one of the most extreme and unique planetary systems we've encountered so far. Positioned in an incredibly tight orbit, it is situated at a mere 0.015 astronomical units, AU, from its star. To put that into perspective, it's closer than Mercury is to our Sun by a factor of nearly 20. The results of this extreme proximity are nothing short of mind-boggling. A year on 55 Cancri a lasts only about 18 Earth hours. In other words, it completes an entire orbit in less time than it takes for us to watch a movie. But that's not all. With such a short orbital period, this exoplanet moves with lightning speed, racing through its orbit at a velocity that challenges our understanding of planetary motion. One of the most intriguing characteristics of 55 Cancri a is its presumed tidal locking. A tidally locked planet has one hemisphere perpetually facing its star, while the other is in eternal darkness. On the day side, temperatures soar to unimaginable levels, while the night side remains frozen and inhospitable. This creates an incredible disparity in temperature between the two hemispheres, making 55 Cancri E a true example of extremes. But recent studies have revealed something even more fascinating. Despite these immense temperature differences, the planet's atmosphere or geological features, such as lava flows, may help circulate heat across the planet, redistributing thermal energy in a way that reduces the expected temperature gap between the two sides. This finding could completely transform how we think about tidally locked planets and their atmospheres. 55 Cancri E's extreme conditions are a direct consequence of its proximity to its star. With its blistering temperatures, this planet is one of the hottest exoplanets ever discovered. The side of the planet facing its star can exceed temperatures of 2,000 degrees Celsius, 3,632 degrees Fahrenheit, a level far higher than any planet in our own solar system. This intense heat is a result of the star's powerful radiation, which the planet absorbs due to its close orbit. But it's not just the day side that is extreme. The night side, in contrast, is a world of eternal darkness and frigid conditions. Scientists are studying this stark contrast between light and dark, hoping to gain insights into how planetary atmospheres react to such extreme radiation. However, what makes 55 Cancri E even more captivating is the potential for atmospheric or geological mechanisms that might help redistribute heat around the planet. One theory is that supersonic winds could be transporting heat from the day side to the night side, mitigating the severe temperature extremes. Another possibility is the presence of molten lava, which might flow across the planet's surface, circulating heat in a way that creates a more uniform thermal distribution. This research is still in its early stages, but the implications for understanding planetary atmospheres and the behavior of exoplanets are profound. In addition to its extreme environment, 55 Cancri holds the distinction of being a super-Earth, a rocky planet significantly larger than Earth, but smaller than the gas giants we typically think of when considering exoplanets. Its size and composition make it a fascinating subject for astronomers, as it offers a rare opportunity to study planetary atmospheres and the impact of stellar radiation on planetary climates in ways that we can't observe on Earth. For all these reasons, 55 Cancri E continues to capture the imagination of scientists and astronomers alike. As we continue to learn more about this extreme world, it may provide invaluable insights into the nature of exoplanets, their atmospheres, and the potential for life in other parts of the universe. In the vast expanse of the cosmos, 55 Cancri A opens up a unique window into understanding planetary formation and composition. With a mass about 8 times that of Earth and a diameter twice as large, 55 Cancri E provides scientists with an unprecedented opportunity to explore the properties and behaviors of rocky exoplanets under extreme conditions. This discovery has reshaped our perception of the diversity of planetary types within our galaxy. At the core of this exploration lies the planet's extreme proximity to its host star and its phenomenally short orbital period. These factors together create a natural laboratory for studying the effects of intense stellar radiation and tidal forces on a planet's atmosphere and surface. The conditions on 55 Cancri A are truly inhospitable, with temperatures on its day side believed to exceed 2,000 degrees Celsius. These scorching conditions could lead to a surface dominated by oceans of molten lava or even vaporized rock in the atmosphere, offering a stark view of what can happen when a planet is subjected to extreme stellar forces. But there's more to this planet than just its hellish surface. The intense heat and powerful radiation create an environment ripe for the study of heat distribution processes, atmospheric circulation, and surface lava flows. Scientists are particularly interested in how these processes might mitigate the drastic temperature disparities between the planet's day and night sides. Through this, 55 Cancri E has become a critical subject in the ongoing research to better understand planetary atmospheres and the physical characteristics of rocky exoplanets under extreme environments. Additionally, the discovery of 55 Cancri E, along with ongoing observations using both radial velocity and transit methods, underscores the growing importance of multi-technique approaches in exoplanet research. This dual-method discovery not only confirmed the planet's existence, but also provided rich insights into its characteristics, paving the way for advancements in observational technology and methodologies. By continuing to observe and study this planet, scientists aim to refine their models of planetary atmospheres, surface compositions, and the potential habitability of other rocky exoplanets that may reside in similar extreme environments. Now, shifting focus to another fascinating world, Kepler 16b stands out as one of the most captivating discoveries in the realm of explanetary science. Located approximately 200 light-years away in the constellation Cygnus, Kepler 16b orbits not one, but two stars, a configuration that was once thought to be purely fictional. This planet's unique orbit around a binary star system evokes the imagery of Tatooine, the twin-sunned planet from the Star Wars saga. Indeed, Kepler 16b offers real proof that planets can exist in binary star systems, defying expectations and expanding our understanding of planetary formation. Kepler 16b is a gas giant roughly the size of Saturn, with a mass about 1/3 that of Jupiter. Its orbital journey through the binary system involves completing one full orbit around the two stars in approximately 229 Earth days. The planet's orbit takes it around the barycenter, or common center of mass, of the binary system, which consists of a K-type orange dwarf star and a smaller, cooler M-type red dwarf. This intriguing arrangement of two stars leads to a dynamic, shifting light environment on Kepler 16b. The planet alternates between periods of doubled sunlight and times when one star partially eclipses the other, casting complex shadows and altering the ambient illumination. These fluctuating light conditions provide a truly exceptional opportunity to study how a stable planetary orbit can persist in a more complex gravitational field. Kepler 16b's discovery via the transit method, where it crosses in front of both stars as seen from Earth, offered an unprecedented amount of observational data. These transit events have allowed scientists to measure the planet's size and orbit with remarkable precision, demonstrating the versatility and capability of modern exoplanet detection methods. This discovery has also revealed the adaptability of planetary systems, showing that stable orbits are possible even in more complicated celestial setups. Kepler 16b's journey through space is a testament to the diversity of exoplanetary environments, offering us a tantalizing glimpse into the variety of planetary systems beyond our own single-star solar system. The discovery of Kepler 16b would not have been possible without the meticulous observations of NASA's Kepler Space Telescope, a tool designed to detect exoplanets by measuring minute dips in starlight as planets transit their host stars. What sets the discovery of Kepler 16b apart, however, is its remarkable orbital relationship with two stars. This binary star system offers an extraordinary example of how planets can maintain stable orbits in a multi-star environment, marking a groundbreaking moment in exoplanet research and demonstrating the endless possibilities of planetary formation in the universe. In a scenario once relegated to the realm of science fiction, a groundbreaking discovery emerged from the depths of space. The process of uncovering this remarkable find began when the Kepler Space Telescope, renowned for observing thousands of stars simultaneously, recorded a peculiar and periodic dimming in the light emitted by a binary star system. Located 200 light-years away in the constellation Cygnus, this phenomenon was the first clue that something extraordinary was unfolding. At first glance, these periodic dips in light were attributed to the two stars in the system periodically eclipsing one another. However, further analysis revealed something far more complex. In addition to the stellar eclipses, a third smaller object was also passing in front of the two stars, casting its shadow on their light. This third body was identified as Kepler 16b. What followed was a meticulous investigation, confirming that these periodic transits were consistent with a planet roughly the size of Saturn, orbiting the two stars at a distance of nearly 0.7 astronomical units. Through Kepler's meticulous light curve measurements, astronomers were able to calculate the orbital period of Kepler 16b with impressive precision. This planet completes its circuit around the binary star system in just 229 Earth days. The detailed data provided not only confirmed the existence of Kepler 16b, but also offered unprecedented insights into the stability of planetary orbits in multi-star systems. The discovery of this planet marked a pivotal moment in our understanding of celestial bodies that exist in binary systems, expanding our concept of where planets can form and survive. Before Kepler-16b's discovery, the idea of planets maintaining stable orbits in binary star systems was largely speculative. Yet, the data from Kepler-16b revolutionized this perception, demonstrating that planets could indeed thrive in these gravitationally complex environments. This finding reshapes our understanding of planetary formation and orbital mechanics, as it shows that not only is life possible around a single star, but it may also be viable in systems with multiple stars. One of the most significant aspects of the discovery of Kepler-16b is that it directly orbits two stars, a feat never before witnessed in such detail. The binary system consists of a K-type orange dwarf and an M-type red dwarf, both smaller and cooler than our Sun. Kepler-16b orbits around the common center of mass of these two stars at a distance of about 0.7 astronomical units, completing one full orbit every 229 days. Remarkably, this planet maintains a stable, nearly circular orbit despite the dynamic and intricate gravitational forces of its two parent stars. This stability within such a complicated system offers vital insights into how planetary orbits might behave in environments with multiple stars, which is crucial when considering the possibility of life in binary star systems. Planets orbiting two stars could experience extreme variations in climate and seasons, as the gravitational pull of both stars would influence the planet's position and orbit. This raises intriguing questions about the habitability of such systems and the conditions under which life could potentially emerge. Moreover, the discovery of Kepler-16b, identified through the transit method, allows for detailed observational data about the planet. As Kepler-16b crosses in front of both stars, scientists can measure its size, mass, and orbital characteristics with remarkable precision. The discovery not only validates theoretical models predicting the stability of circumbinary planets, but also suggests that such planets may be more common than previously believed. The importance of Kepler-16b cannot be overstated. Its discovery marks a monumental step forward in our understanding of the universe. Not only does it provide crucial data on how planets can maintain stable orbits in binary star systems, but it also challenges the assumptions about where planets can form and survive. As we continue to explore the cosmos, discoveries like Kepler-16b remind us that the universe is full of unexpected and wondrous possibilities, far beyond what we could have imagined. Kepler-16b stands as a monumental milestone in the exploration of exoplanets, opening up new frontiers in our search for habitable worlds. Orbiting not just one, but two stars, this gas giant offers a fascinating glimpse into the complexities of planetary systems that differ radically from our own. Its position within a binary star system, comprising a K-type orange dwarf and an M-type red dwarf, results in a highly dynamic and fluctuating climate that challenges our understanding of planetary behavior. The existence of two stars has profound implications for Kepler-16b's climate, creating a unique environmental dance between light and darkness. As the planet orbits the barycenter of its twin stars over a period of 229 Earth days, the distances and relative positions of the stars shift continuously. This dynamic motion leads to dramatic changes in the amount of sunlight the planet receives. At times, both stars shine on the planet simultaneously, effectively doubling the amount of sunlight and resulting in warmer periods. On the other hand, there are moments when one star may eclipse the other, causing a reduction in sunlight and creating cooler intervals. Such fluctuations in solar radiation lead to complex temperature patterns, which can significantly affect Kepler-16b's atmosphere and surface conditions. In addition to this variability in sunlight, the dual star system also gives rise to intricate weather patterns and atmospheric dynamics. The alternating heating effects from the two stars may cause varying wind patterns, cloud formations, and even storms. These changing solar radiations trigger shifts in atmospheric pressure, which could result in significant weather disturbances. Although Kepler-16b is a gas giant and not a terrestrial planet, its climate serves as a valuable model for studying the behavior of exoplanets in binary star systems. The insights gained from this study could help scientists predict the potential for habitability and atmospheric stability on other planets in similar systems, thus broadening our perspective on the diverse environments that may exist throughout the universe. However, while Kepler-16b presents a compelling subject for scientific study, it is unlikely to support life as we know it. As a gas giant similar in size to Saturn, Kepler-16b lacks the solid surface required for Earth-like life, which typically depends on stable terrain and liquid water. The planet's composition, predominantly hydrogen and helium, does not offer the necessary conditions to support life forms reliant on rocky surfaces or liquid water. Moreover, the extreme climate conditions resulting from the erratic solar input from its two stars make it a volatile and inhospitable environment for life. Intense radiation, unpredictable temperature shifts, and fierce winds would create a harsh atmosphere, further diminishing its habitability prospects. That said, the study of Kepler-16b still holds immense value in refining our understanding of habitability. It challenges conventional criteria for life and pushes the boundaries of how we define potential environments for life beyond Earth. While Kepler-16b itself may be inhospitable, the moons that orbit such gas giants may present a different story. If Kepler-16b had large rocky moons with stable atmospheres, these satellites could, in theory, provide conditions suitable for life. The climate effects induced by the binary stars could be better understood through the study of these moons, offering critical insights into the habitability of exomoons in similar star systems. Thus, while the planet itself may not support life, its study can inform our search for habitable moons in other solar systems. In the grand scheme of cosmic discovery, Kepler-16b serves as a reminder that the universe is vast and teeming with potential. As we continue to explore the many exoplanets scattered across the galaxy, each discovery brings us closer to understanding the possibilities of life beyond our solar system. These distant worlds are not just scientific curiosities, they represent the unknown, vast expanses waiting to be explored. With each new exoplanet we encounter, we are reminded that the story of the universe is still being written. As we look to the stars, we are left to ponder what lies beyond the horizon. What if we are not alone in the cosmos? Could there be other beings gazing up at their night sky, wondering if we are out there too? Let us know your thoughts on this captivating topic. Don't forget to subscribe to our channel Starflux for more fascinating insights into the universe. The journey of discovery is just beginning, and the next chapter could reveal secrets we can scarcely imagine.